direct questions for the speakers, and we'll also try to accommodate some questions from the chat box. So I would hand over to my younger colleague Abhijit Prasad to further go on with the session. So still we have few minutes, Abhijit. If you want to say something, you can please go ahead.
Thank you, Abhishek. I would just like to thank the hosts for asking me to co-chair this session. I think we have all, since it's the fourth day of the session, so I think everybody is used to the announcements. That I'll just repeat the same, that I'll request the audience to stay muted during the talks, and as usual, after the talk, the questions can be typed in the chat box or asked through the raise hand feature. And so I think we can wait for a couple of minutes and then start.
Sure. Yeah. So formally then we can start.
Go ahead. Now at clock here it's 8:27. Yeah, maybe we can wait for 3 minutes.
Oh, yeah. Okay. So in the meantime, I would try to contact Vidya if he's there.
Abhijit and Abhishek.
Yeah.
Actually, for me, can you give me a warning at exactly at 20 minutes?
Okay.
Because I prefer that. That would allow me to probably hurry up.
First talk today will be given by Paul Charbonneau from the University of Montreal, who will be speaking on solar and stellar dynamics, consensus and divergences. So this talk is an invited talk for 30 minutes. So the last 5 minutes will be for questions. So with this, I invite Paul to start the talk.
Okay. Well, good morning, Bangalore. It would have been, of course, nicer to be there in person, especially since it's -20 outside here today. It is actually quite a pleasure and an honor to give a talk at this meeting for the 50th anniversary of the Institute. My topic, talking about solar dynamo and modeling, is one for which there is quite a bit of expertise in India and lots of very proficient practitioners. Many of them actually are going to be speaking at this in this symposium. So that makes it even more fun. And I would like to thank the organizers for inviting me to do this. So here we go. So I changed a little bit the title from what I think you had in the abstract. I called it Convergences and Divergences. The field of dynamo modeling for the sun and stars, especially, but also for other objects, has been quite active in the past few decades. And when I was invited to do this talk, I thought I picked basically two things in which there were some pretty exciting developments, I think. And I will talk about these two things, two different types, two approaches to solar dynamo modeling. And I will try to highlight both what I call convergences and divergences. I mean, some of these things have led to convergence where we start to agree on stuff, while others have led to situations where we suddenly think that we no longer understand things that we thought we understood, which is an interesting situation as well. So maybe that doesn't make too much sense now, but hopefully as I proceed, you'll get a better idea for what I mean by this. So let's start with something that I think, all agree upon in the context of dynamos, namely that in a star like the sun, in the interior of the sun, the cyclic regeneration of the sun's magnetic field takes place through dynamo action, which is basically described for solar interior condition or stellar interior condition by the magnetohydrodynamic equation. This is really Faraday's law with, the electromotive force given by this motional EMF, the dissipation part. Now, I can dot B into this and construct an energy equation, which is at the bottom here, for the magnetic energy within my volume. And there's really three contributions to this. This is a boundary term, which we usually take to be zero, assuming there's no sources coming into our system. This is the enemy, this is dissipation, this always destroys the field, and the action is here. And the reason I show this is basically the flow, and this is the Lorentz force. So this is telling you that the stuff that amplifies the magnetic field is really kinetic energy of the flow being transferred to the magnetic field, to magnetic energy. So this is really the essence of a dynamo, transferring kinetic energy into electromagnetic energy. And it's a fundamentally nonlinear process, and that's a very important thing I'll come back to a few times in the course of this talk. So I would say that this is probably my only slide where I can write consensus, where everybody agrees on this, or nearly everybody agrees on this, nearly enough that we can call it a day. Now, if you start to decide, you want to pick some flows that you will put into the image induction equation, then I have induction and amplify and the magnetic field and I have polarity reversals and all of this. It turns out that we have actually an abundance of flows and mechanisms in the context of a star like the sun that will do the trick. We can shear an existing colloidal field. This is known for quite a while. It works really well. Turbulence, convective turbulence in the outer layers of the sun and stars can generate electromotive forces that will also contribute to amplification of the fields. There are various instabilities that can be affected by Coriolis force that can give you induction as well. And then, as magnetic flux ropes rise through the convection zone to emerge as sunspots, or so we think, they get affected by the Coriolis force as well. They can get twisted. That generates a dipole moment that can then be released by the decay of active regions and contribute as well to the amplification of the sun's magnetic field. So we have an abundance of mechanism. This one, the shearing of a dipole, say, is something that, pretty much everybody puts into their dynamo models. But then there's some disagreement or argument as to which of these processes, and there are many more than that, but these are the main ones, which are important or even dominant. So there's a certain, in the past, maybe 10, 20 years, people have been exploring a lot of these mechanisms, and we have a lot of potentially viable inductive mechanisms, especially associated with instabilities and turbulence that could do the trick. Now, mean field dynamo model used to be what solar dynamo and stellar dynamos were about. It is based on something called scale separation, which those of you who've done hydrodynamics have encountered when you basically you split your flow into a large scale and small scale, plunk that back into your fluid equations, average over some suitable intermediate scale, and out pop the Reynolds stresses, the stuff that basically capture the influence of turbulence on the large scale flows. You can do the same thing with the induction equation, where you go break up the field in a large scale part and a small scale part that averages out to 0 when you average. Same thing with the field. You put that into the induction equation, you average, and you get, this is something most of you are probably aware of, you get an induction equation for the mean field that looks exactly like the original induction equation, except it picks up this extra term, the turbulent electromotive force, which again captures the effect of small scales on the large scales in the same way that Reynolds stresses capture that in the hydrodynamical context. If you want to close these equations, you don't want to deal explicitly with the small scales. The next step is to basically develop this electromotive force as a sort of power series of the mean field. And these tensors here show up. And this is basically all that's left of your turbulence. The statistical properties of the turbulence are basically hiding in those tensors. Now, it turns out that if you make certain assumptions as to the statistical nature of that turbulence, you can actually compute these tensors in the most simplest case of homogeneous isotropic turbulence, but that lacks reflectional symmetries. These two tensors, if you have isotropy, they just become diagonal. And these diagonal elements, you can compute. The first term in the expansion, the alpha term, ends up being proportional to the kinetic helicity, and the second one is going to be proportional to the turbulent intensity. Now, when I took a graduate astrophysical fluids course a long time ago from a guy, early 80s, from the guy named Jean-Louis Tassoul, who really knew his stuff. And when we talked about solar dynamo, that's more or less where we ended in terms of theory with mean field electrodynamics, because back then it was thought to be the way to talk about the solar dynamo. And that has changed. That has changed in good part because of Helio seismology, who demonstrated that the sort of flows that people used to put in to construct dynamos based on mean field theory were not the ones who were observing inside the sun. Another problem, of course, with this is that turbulence inside the sun is not homogeneous, it's not isotropic, and it's not weakly influenced by the magnetic field. There were also some theoretical concerns as numerical simulations started to be able to address these issues. It became clear that mean field electrodynamics was a bit, dodgy, to say the least. And that has actually spurred the revival and the development of new ideas, or revival of old ideas. One I want to talk about a bit, but not too much, because you will get, I think, quite a few other talks in this. We'll get quite a few other talks in this session, and I don't want to steal anybody's punchline. But there is this one class of model that goes back to the late 60s, and that was, in some sense, revived in the late 80s, early 90s. And I've put a few of the first papers that really contributed to that revival down here. And they're basically based on this notion that as sunspot pairs, bipolar magnetic regions, emerge at the surface with a tilt with respect to the east-west line, this tilt corresponds to a dipole moment. And as the active region decays, you can release that dipole moment, carry it to the pole with diffusion or large-scale flows, and reverse the surface dipole that way. This was actually observed already back then. And that can be, one half of a dynamo, the other half being the shearing of a dipole. Now, the way we build these models, we in some sense, we use mean field theory, but we throw away this alpha tensor and we replace it by this surface mechanism that's supposed to regenerate the dipole. So that's how these models typically are built. And they have undergone quite a bit of development in the last 10, 20 years. And again, since I don't want to steal anybody's punchline, I'll simply say that they provide at this point, at that level of complexity, probably one of the best representation of the solar dynamo in the context of these mean field type models. And in particular, we understand now that cycle-to-cycle fluctuations can be well understood in terms of the scatter in the property of active regions, their pole separation, their flux, their tilt. Those models have also been used rather successfully to try to predict upcoming cycles, and you will hear more about cycle prediction in a later talk. the idea, the basic idea goes back to like at least the Chatin et al., 1978 or something like that. But it's more recently that it's been really truly built into dynamo models, and that has led to a successful prediction of cycle 24. This is an example of a surface flux transport model based on the Babcock-Leighton mechanism. And what I'm showing you on top is a sort of a time latitude diagram covering 4 cycles. This is a model simulation. It's not the real thing. The bottom thing is a diagram showing you the density of emerging sunspots over a period of about 40 years. Excuse me. And I picked this little sequence because it looks an awful lot like cycle 22, 23, 24, 25, right? You get 2 fairly high amplitude cycles, an extended minimum and a weak asymmetric cycle. It just kind of looks like the cycle 24 event. But the point being is that since we can observe the surface, we can really develop and calibrate these models to look an awful lot like the sun. So that's about as good as it gets at this level of complexity. I would call that convergence. I mean, there's still things that are not quite right with this, but in terms of looking like the sun, these things are really getting there. So that's very encouraging. There are still problems. Most of these models are still fairly simplistic geometrically. They're often only 2D axisymmetric. This is improving. I've put you some papers there where these improvements are starting to show. Mostly kinematic, very little nonlinear back reaction. A few very nice papers where this was tried. I've given you here. The back reaction on small scale flows, as in all of these models, is also very simplistic. But again, some attempts to do a bit better. And this idea of using the polar field as a precursor, which is a feature of these models, is actually found in other types of dynamo models as well. But this is also a good handle, a reality check, excuse me, on all of this. So that looks pretty good and nice and fine. On to numerical simulations. When you do a real full-blown global numerical simulation of solar convection, well, you don't catch all the scales that you need to catch. You don't catch all the time scales. You don't catch all the spatial scales. But at least you are solving what we believe are the full real dynamical equations. In mean field-like models, we basically solve only the induction equation. And we don't solve explicitly for energy conservation, for momentum conservation. The very important Lorentz force, remember, it's the work you do against that is the essence of the dynamo process, is parameterized or ignored altogether or extremely simplified. So when you do a simulation, at least, you can actually, for the scales that you resolve, you actually have the dynamics in principle done correctly. So you make these very fancy pictures, that's just publicity. But I want to show you an example of a simulation. And it's one done in my group, but it doesn't matter. I just had it. That's why I show you this one. What you're having up there is basically the zonal, the toroidal component of the magnetic field rendered as a color scale on the full sphere. Here I'm giving you a meridional slice of the zonally average version of this. And the 2 bottom diagrams are showing you the toroidal field at the base of the convecting layers as a time latitude diagram. And the bottom one here is I've made a radius time diagram where I slice my simulation at mid latitudes. And this is a small animation, and you will see a full polarity, you will see a polarity reversal in a fully turbulent simulation with all the nonlinear dynamical feedbacks that should be there, included. I'll play it twice because it kind of runs a little on the quick side. So you see we start with yellow on top, green at bottom, positive, negative. And the thing is very turbulent. It's very, it looks noisy. I don't know what it looks like from your end, but we still get a fairly stable toroidal field structures, reversing polarity synchronously across hemisphere. If you look at these time latitude and radius latitude diagrams, clearly there are problems, right? The activity is at too high a latitude. We get very little equatorial migration, but we do get a very regular cycle, anti-symmetric about the equator, very well coupled across hemisphere. We do get accumulation of strong magnetic fields at the base of the convection zone. These are all things that we find in mean field models, and we still find them in those kinds of simulations, in some of them at least, with all the dynamics actually present. So I would call that convergence. Still lots of things that we need to improve on, but at least it seems to be heading the right way. Now, I can go farther than that. I can actually take one of these simulations and test mean field theory, right? I can go in there, I can compute the turbulent electromotive forces out of the simulation by measuring the flow, measuring the field, the fluctuation part, averaging. I can compute all of these things, right? And I can check whether that expansion I've made actually makes any sense, because I also have the mean field, and I also have all the derivatives of the mean field. So I can then compute all these things and compare them to what we get out of, or what we put into mean field models of various kinds. And it's an interesting exercise. It's a complicated exercise. There's various ways of doing it. And I want to show you a few things that are robust in the sense that they show up not only in our simulations, but very different groups using different codes, different analysis methods to get these tensors tend to find a fair amount of things that are the same. So there is divergence and there is convergence in this game. The first divergence is that these tensors, they're not at all nice diagonal tensors that we like to use for isotropic situations. They're full tensors, so that's an important divergence. In the language of mean field theory, these simulations behave like what we call alpha square omega dynamos. Turbulence contributes to the generation of the toroidal field as well, not just the poloidal one. So there are definitely divergences from the picture, but they are surprising convergences. This is turbulent diffusivity as I extract it from a simulation. This is turbulent diffusivity I reconstruct from just knowing the turbulent intensity, as if turbulence was isotropic, homogeneous, and all of that jazz. And, it looks not so bad. I mean, the amplitudes that I get out of the simulations are around 10 to the 8 meters squares per second, which is what, we tend to use in mean field theory. It goes a bit higher as well. Peaks in the middle of the convection zone, that's true for that one as well. So this is, I would call that convergence. We seem to get the right kind of turbulent diffusivities, the sort that we know we need to use in most mean field and mean field-like models. This is one of the components of one diagonal component of the alpha tensor. That's the key one to regenerate the dipole. And again, it looks pretty good if you compare predictions of mean field theory based on homogeneous isotropic turbulence. And if you look at what you pull out of the simulation, the scale is good as well, a few meters per second. That makes sense. That's what we typically put in to the dynamo model. So I would call that convergence as well. There is this strange factor of 5 difference in amplitude, which we can fix by assuming that the coherence time of the turbulence is quite low. This is kind of a technical point, but this thing is very hard to measure out of a numerical simulation. Most people assume that this is equal to the turnover time of the convective eddies. But if we make it a bit smaller, then the amplitude fit is actually quite good. That's more of a technical point. I can also do that fit cycle by cycle. I can fit on the maximum part of the cycle, the minimum part of the cycle. I have a simulation that runs stable for 40 cycles. So I can actually measure one cycle after the other and one hemisphere at a time. What's the strength of this alpha effect at solar min and at solar max? So I see quenching of the alpha effect in simulations like this. It is very fluctuating, but you definitely see, well outside of the error bars that at solar max, which is red and yellow here, your alpha effect is significantly smaller than at minimum phases. If I plot that against magnetic energy density, you get this decreasing curve again, which is what you expect. And then you take a deep breath and you try to fit these very ad hoc quenching formulas that again are, we tend to use that all the time because it does the right thing in simpler model. And you don't get a very good fit. These are not really fit, this is more by eye, but the trend is there. Some of these so-called strong quenching formulas, if I put magnetic Reynolds numbers of the type that I see in my simulation, they actually, excuse me? Oh, okay, right, okay. They actually give you more or less the sort of quenching that we expect. An interesting point to note is that even at solar minimum up here, we are in the steep part of the quenching curve. So even models that are at the weak phase of the large-scale field are actually strongly quenched. Again, it's a strongly nonlinear system. So I would call that convergence of sorts. I couldn't believe it when I saw it myself the first time, that we could actually get some sort of semi-sensible fit using these totally arbitrary formulae. I'll skip that part because I'm running a little out of time. I really wanted to talk about this. This was an exciting, still is an exciting development of the last decade, where simulations that generate magnetic fields inside the convection zone at a very high, fairly high resolution in turbulent regime generate these magnetic tube-like structures that partly rise buoyantly, partly are entrained by the convection, and rise at the surface, maintaining their orientation and even showing up with tilts that look a bit like what we observe on the sun. Joy's law, for those who knows what this is, the leading member of a bipole is closer to the equator. Now this is out of a numerical simulation. This is a form, I would call it a form of convergence. It looks an awful lot like the sun. It's also a divergence because we used to think that these things had to be formed in the tachocline at the base or below the base of the convection zone. We have thin flux tube models that beautifully reproduce, the tilts of active regions and things like that. And now it seems that we can generate these guys also in the convection zone without a tachocline. That has important implications when you start applying these ideas to stars other than the sun. Stellar cycles, again, you can run simulations at varying rotation rates, varying luminosities, and you can look at what sort of cycles you get. And it's extremely sensitive. There's a quantity called the Rossby number, which measures the relative importance of a convection timescale versus Coriolis force timescale. It's believed to be a key parameter in dynamo. And based on mean field models, the idea was that somehow the cycle period had to scale with that Rossby number, the faster rotating star at shorter period cycles. If you generate sequences of solutions in which you measure your cycle period and you measure your Rossby number, you find something that goes the other way. The more rapidly rotating stars have longer cycles in this range here, where we get cycles a bit like the sun. And again, different groups, like if you can go check out this paper, using completely different simulations, different ways to estimate the Rossby number, find almost exactly the same exponent. They find 1.4, I think, instead. So this is a huge divergence compared to what we thought we understood about the way the cycle period scales with various input or
All about 1 more minute.
Okay, diagnostic parameters. So plenty of things to do on the numerical simulation side of things as well. We're a long way from the physical regime we want to be in. We don't have a photosphere. We don't really have a Babcock-Layton mechanisms. We have a wide variety of cycling behaviors, sensitivity to numerical details, things like that. So again, a lot to do. How do we make any sense out of this? Well, I would say that the most pressing matter is really to figure out what sets the cycle period. Now, this is a very fundamental, basic idea. The cycle period is fairly easy to measure, even in stars, if you have long enough data sets. In these kinematic mean field models, it's fairly easy to figure out what sets the cycle period. Mean field models, Babcock-Layton variety of the mean field models. In simulations, it turns out to be much harder. It tends to be link to the nonlinear back reaction on the flows in a very intricate way. So I find it quite sobering that we still really we can't say right now that we really understand what sets the cycle period in a dynamo, even a fairly regular one like the sun. There is hope with helioseismology giving us a handle on that nonlinearity. Interesting things as well with space missions observing the solar pole. We might be able to disentangle flux emergence from flux submergence. And, you know, we have to continue modeling the tachocline if we want to have a chance to understand maybe the origins of some of those sensitivities that we observe there, and especially when it comes to long time scale behavior. So these would be my top 4 in terms of what we want to do. I can only at this point say thank you for your attention. And these are the faces that went with some of the names that I flashed on my first slide. You can see that most of them are smiling. So if anybody out there is looking for a PhD project or something like that, you know, going into the dynamo area is obviously not too traumatizing. All these people came out of it looking pretty happy. So thank you all.
Thank you, Paul, for this informative talk. We have a couple of questions. So Arnab, would you want to ask a question?
Yeah, sure. So Paul, thank you for this great overview of the subject. And it's very impressive to see this convergence between mean field models and what you get out of these simulations. Of course, in the simulations, the main thing missing is that you do not get this equatorward propagation. And in mean field models, that crucially depends on meridional circulation, which I suppose is very difficult to get in full simulations because it comes from slight imbalance between this thermal wind term and the centrifugal term. So would you say that that in the failure of simulations to get this is due to not getting meridional circulation properly, or do you envisage that in the near future things will improve?
Hard to tell. I should first say that even like the simulation, the one simulation I showed you that I used for my analysis did not show equatorward propagation, but other simulations show it. So it's not like they never show it. That one that we were looking at didn't. In terms of the flow, I think that at the base of the convection zone, an equatorward flow is probably a fairly robust thing, simply because of overshoot affected by Coriolis force. It is certainly the case that very few of these simulations, if you run them in a regime where they get you more or less the right differential rotation, they do not give a nice single cell meridional flow like you and I like to use all the time. That is certainly true. There's a weird trade-off if you change parameter regime so that you get this nicer one cell flow, then you don't get an accelerating equator anymore. You know, there's a trade-off, and you might be right. The key might be to get that proper pole to equator temperature difference to build up autonomously in the simulation to give you that thermal wind effect. That's quite possible.
Okay, thank you.
Maybe one more quick question. Matthias, do you want to ask?
Paul, you showed that the dynamo solutions you found in your 3D simulations follow more or less the strong quenching regime. Does this mean that the solutions which are currently found in 3D simulations will not survive when you move to more realistic Reynolds numbers?
That's possible. We'll only know when we get there. We did have runs without a tachocline though that went to higher Reynolds number by maybe a factor of 3 and 4, and we still got cycles. They actually had equatorward propagation, but we lost the nice hemispheric synchrony. The hemisphere started to decouple. So yeah, there's lots of things to be explored at very high resolution.
Devendra, I think, yes.
I thought I heard something, but
yeah, I see a background noise also. So Paul, so if you look at the nature of dynamos, we believe that it is probably different across different stars, and maybe also changes due to the evolution of a particular star over its, due to changes in its convection zone properties. So under the circumstances, do you believe it's appropriate to take stellar observations from various stars and apply it to constrain the current state of the solar dynamo? Or is that a bit too much?
I think that if you don't go too far from the sun in the sense of rotation rate or structure, mass, or luminosity, I think it's legitimate. It is certainly the case that not just us, but many groups who do these things find rather extreme sensitivity. I showed this, I didn't have time to discuss it too much, but I flashed this plot where within a factor of 10 in Rossby number, we had 3 different kinds of dynamo behaviors. We had steady fields, we had solar-like oscillating fields, and we had these very fast cycles. All this happened within the factor of 10 in Rossby number, which is peanuts. If you think of the range of Rossby numbers that you get in a stellar sample. So yeah, we certainly have to be careful if we go to stars that are like significantly less massive or more massive than the sun, and so on and so forth, much more luminous. Yeah, but there's more and more good stellar data coming around, and that's of course very exciting. Even including measurements of differential rotation are starting now on stars from photometry. That's very, very interesting.
Okay,
I think
thanks.
there are some questions in the chat box also, Abhijit.
Okay, what's the difference between coherence time and turnover time of eddies? So the turnover time would be the time it takes a convective, if you imagine an eddy as being a nice little roll, so it's the time it takes to go around once. So that would be the turnover time. The coherence time is what's the lifetime of an eddy? Is it gonna last for a whole rotation? Is it gonna turn 3-4 times around? Is it just gonna go half a turn and then disintegrate and reform into something else? That would be the coherence time. That was a question. Yeah.
Thank you, Paul. I think we should move on to the next talk.
Okay, sorry. Okay, fine.
Yeah. So the next talk would be by Irina Kitiashvili from NASA Ames, who will be speaking on global solar activity forecasting using synoptic magnetograms. So Irina, if you can share your screen now.
Yeah, I believe you should see my screen now, right?
Yes. And I should give a warning after 12 minutes. Is that okay?
Sorry, how much time I have?
So we have 15 minutes and I should give you a warning after 12 minutes.
Okay, I just try go to presenter mode, but for some reason, yeah. It looks good now? Okay, I hope so.
Yes, that's good.
Hello, everybody, and I'm really happy to participate in this conference. And I would like to say thank you to organizers to give me opportunity to discuss about my vision on a global solar activity forecast. And as all of us know about problem with uncertainties, both in models and observational data. And in fact, in my work, I try apply data simulation technique, in particular ensemble-Kalman filter, to do prediction of global solar activity. In this case, we can consider observations as observations which describe like through conditions with some error. In same way, we can also describe our model, like it also can predict some evolution of our true conditions, say true solar activity with some error. And problem is how we can estimate uncertainties and errors both from observations and our models. And because it is quite tricky thing, so we try to estimate such deviations both from observations and our models using Kalman gain to correct our solution according to more correct state. But because it is a non-linear system, in fact, we have a lot kind possibilities. We can estimate ensemble of different states, and from this we can estimate the best condition of our system according to our previous analysis. Okay, next step, of course, it is a physics-based model. And in this case, I use classical Parker mean field dynamo model. And also I use a third equation, which describes a variation of magnetic helicity and the interaction with a large-scale magnetic field. But in a difference with previous talk, I'm not going to present fancy 2D models. It will be just, everything is done just in 1D formulation, essentially dynamical system. And the reason for this, because it is too many uncertainties, how we have to process data, how we have analyzed data, how we can restrict our solutions to this. I'm not going to discuss very much about it, but I will love to talk about it. What prevents us to move quickly from 1D to 2D, but we are getting ready. I'm getting ready to this. Okay, but before this, because we have long time series of sunspot number, of course, we have to test if this approach even work. And what is done, in fact, we did a kind of like test predictions for last 10 cycles. And the reason for this, we first develop kind of methodology how we should work with solutions, how we should process our data. But also we need somehow calibrate our model to avoid changes model parameter from cycle to cycle. And you see optimal solution for all cycles, but still, of course, it is not surprising what we have for some, say, test predictions. For example, for cycle 20, we have, actually we underestimate solar cycle. For 16, we overestimate cycle, but in general, it looks pretty good. We did also in past prediction for solar cycle 24, and it worked pretty well. And I would like point just declining phase. Usually when I see solution like step-like solution, usually I start worry what usually it is indicate what I probably start accumulate errors and errors getting too large. And in fact, it indicates for me, probably I should not trust very much this part of solution. It is kind of good constraint for myself to be careful. Surprisingly, for cycle 24, it worked pretty well, even on declining phase. But as you see, even in test prediction, for example, for cycle 22, you see kind of similar behavior. And for this test prediction, for example, cycle predicted a bit longer than it was actual one. Also, we did testing capability of this model in terms of prediction, early prediction of solar activity. In fact, we found what we potentially be able to make early prediction capability only during polar field reversals. But it is also some restriction in case, say, if polar fields in different hemispheres change with some lag, as long getting longer. So I'm getting, I can very quickly, I start again very quickly accumulate errors, and of course I can get really wrong solution. Okay, next problem, because of course I don't want to spend much time on sunspot number based predictions. I would like to move to magnetograms. But before this, I would like to test how affect short time series on my predictive capabilities. For this, I did test predictions for a few last cycles. And what I did, I just assume I have 8 solar cycles of available data. did like test forecast, and after that I start to remove cycle by cycle, figure out how it will affect on my solution. And this test is critically important because especially when I go at the solar minimum, sometimes I have to make decision which observational point, last observational point I should get. But so you see, for example, for like, I don't know if you can see my mouse, but say I have some choice. And sometimes, because it is nonlinear system, I can get very strong cycles, very weak cycles, and question is how I can decide which is right. And after our testing, we develop clear criteria how we can choose our solutions to make decision which is correct. And after that, I'm ready to move to magnetograms. We have only 4 cycles of synoptic magnetic field measurements. And of course, it restricts me to do like a lot of calibration tests and so on. And for this reason, I did tests. I try first predict solar cycle 23 using synoptic data from cycles 21 and 22. And same I can do, of course, for cycle 24 using all available data and using only 2 cycles. First, of course, what I have to do, I have to decompose magnetic field, synoptic magnetograms to toroidal and poloidal magnetic fields. It's shown on the right-hand side. But because we traditionally, when we discuss about solar variability, we usually discuss this in terms of sunspot number. I was interested to compare if I compute sunspot number from, say, this toroidal field, how much it will different from actual sunspot numbers. And on bottom, you see plots for both hemispheres, and green dots correspond to sunspot number computed from toroidal field. And blue one is observed one. Don't be confused with agreement with in the cycle amplitude for cycle 24, because it was normalized to this cycle. But still, you see, as we go to early cycles, we see some strong deviations, especially for South Hemisphere and cycle 22. It just kind of feel what important to keep eye on this. Okay, let's move to forecast, test forecast. And I did the first forecast for cycle 23. And you see like analysis part of first 2 cycles when we have observational data and prediction. And red dots correspond to actual observations, for example, for South Hemisphere. And you see for toroidal field, we can do a really good job up to solar maximum, but strong deviations on declining phase, and pretty good work to predict toroidal fields in the North Hemisphere. But if you look on poloidal, I'm getting close. So if you look on poloidal fields, essentially you see empty dots, it is actual data. You see we did pretty bad job in predicting poloidal fields in this case. You see I start almost immediately gets very strong deviations. I repeat same analysis for cycle 24. Okay, it worked pretty well for toroidal fields. For poloidal field, I have a better agreement for prediction phase. Essentially, I am able to predict for a couple years, but still not the best. And if I include 3 cycles, for poloidal field, I see a quite strong improvement. But as you also may notice, I'm able to predict poloidal field only up to solar maximum. And after that, say, I have very really wrong prediction. Last thing, what I would like to discuss about it when we discuss about sunspot number, in fact, important to note say, for example, for test prediction for cycle 23, if we consider North and South hemispheres, you can see, say, for North hemisphere, I over-predict solar activity and under-predict for South hemisphere. But when we discuss about total sunspot number, just because I sum two uncertain values, I'm get near perfect solution. So it kind of like important note about it. For solar cycle 24, I did a pretty well job to reconstruct solar activity for both hemispheres. But when I just sum results for both hemispheres, I have stronger deviations for total sunspot number. And finally, I just would like show very quickly results for prediction of solar cycle 25. And according to my analysis, solar cycle 25 will be weaker than previous one. I know it is quite different what most of models show. And also this model able to predict what cycle will start at the south hemisphere, what actually we know it is true, but again, to say if it is a correct prediction or not, we should probably wait at least a couple of years, of course. And just to conclusion, I would like to say we right now are getting more and more ready to move to two-dimensional model analysis. And the reason for this, because when you have to do a simulation, it is data what you include in your data assimilation analysis may significantly affect on your results, and it kind of require strong data preparation work. And we are now working on this. Thank you very much, and I will be happy to take any questions or maybe suggestions.
Hello. Hi, this is Pooja from IIA Auditorium. So I have a question. When you are doing a prediction of this solar cycle, most of the time, like as a trained data or the past data, you have used like solar cycle 21 and 22. So my question is, like, if let's say we take more number of solar cycle in the past as a trained data, so would it affect the accuracy level for the prediction, or it would be in a good way to handle, like, because let's say we take 19 or 20, so one maxima, one minima, then 20, 21. So if we take a more number of years in the past to predict the future, so how would it affect the prediction?
Yes, it may significantly improve prediction. A reason for this, because when we are small, it kind of iterative process. We estimate errors first from data what we have. We add a little bit more data and redo this analysis. It's like, you know, iterative process. It why length of data sets very important. And in fact, it is, say, if we compare even test prediction for solar cycle 24, you can see a significant improvement in, say, reconstruction. It's hard to say it is prediction, of course, as we add one more cycle. So it is critical issue. But again, it is question is, say, if you would like go to two-dimensional model, for example, include observations, helioseismic observations, we have just only 2 cycles of data. Question is how we can work with this, because we really don't have room for testing and proper calibration of our model according to observational data. It is biggest issues from my point of view.
Okay, and just a small another question on that, like, so does the like selection of the data, let's say either you predict using the sunspot number or a magnetogram, so selection of the variable will also have any effect on the prediction? Like,
I'm not sure what I understood. In this case, in fact, when I use say sunspot number, I just converted sunspot number into toroidal field. And what is done for poloidal field and magnetic helicity, I just generate these observations from my solution, including some noise, uncertainties, and so on. When I have synoptic magnetograms, I can have more or less real I can describe in more realistic way variations of poloidal and toroidal fields. But I should say for right now, magnetic helicity is still synthetic. It is additional issue that must be solved.
Okay,
Thanks, Irene. So we shall now move on to the next talk by Dipendra Nandi from IISER Kolkata, who will be speaking on solar cycle predictions. So Dipendra, I will be giving you a warning after 20 minutes.
Yeah, please give me a warning at 20 minutes. I would appreciate that.
Okay, thank you.
All right, so good morning, everybody, and good evening to those across the Atlantic or in Europe. So we know that the sun's radiative and particulate output, as well as the frequency of solar storms, vary over the solar cycle, and these are modulated by the magnetic output of the sun. And therefore, having a prior understanding of the amplitude and the timing of following sunspot cycles is considered of great importance in heliophysics. However, it's been a challenging task to be able to accurately forecast the sunspot cycle, as our history for sunspot cycle 24 shows us. So if you look at the forecast for sunspot cycle 24, let me first give an understanding of the normal envelope of possible amplitudes of cycles, which is within this two green red dashed line, barring the minima phases. And then if you look at the range of forecasts for sunspot cycle 24, it spans the entire range of all sunspot cycles ever directly observed. More importantly, two physics-based predictions for sunspot cycle 24 diverged by a wide margin, with one predicting a very weak cycle and one predicting a very strong cycle. And this sort of generated a lot of controversy and debate in the community in whether we actually understand the physics of solar cycle prediction. So let me set the context here. So it is desirable that with assimilation of physical understanding and progress of the sun's interior and the dynamo mechanism, one should be able to move towards predictive models of the solar cycle. If you look at the history of how weather research has progressed, a reasonable degree of consensus has been achieved in climate modeling community, for example. But it seemed like this was eluding the solar physics, the solar dynamo community. However, it's important to note, following this early debacle of sunspot cycle 24, there has been significant progress in our understanding of the predictability of sunspot cycles. This has not necessarily happened in a very linear way, and often we have learned from our mistakes. Today, I'm going to tell you the story as I understand it, in terms of how much we have achieved in terms of understanding whether the sunspot cycle is predictable, and if yes, what is the best way. So let me first outline some outstanding questions that are in my mind coupled to predictability of solar cycles. The first and the foremost question is, are solar cycles predictable? Does the inherent nature of the solar dynamo allow predictability? If yes, then what is the best proxy for predicting sunspot cycles? And do we understand why the dynamo forecasts for cycle 24 disagreed in hindsight? Now, what can we predict about the sunspot cycle, and how accurately, if predictions are possible? And how early can we make predictions of the solar cycle? And what is the early outlook for solar cycle 24? So by the end of this talk, I would have hoped to answer most of these questions for you. So an important point to keep in mind, which is often lost, is that if you look at development in climate predictions, or trying to understand weather from the perspective of predicting it. This field has evolved and matured over half a century. But if you look at attempts to make solar cycle predictions based on physical understanding, this is an extremely new domain where we have been worrying about this pretty much over the last decade or so. And I want to keep the perspective, everybody keep the perspective in mind. All right, so I'm not going to get into great details about the dynamo mechanism, and Paul has done a great job about this, but we typically look at the induction equation as a means to understand a magnetodynamic system, the interactions between magnetic fields and flows in a plasma domain. And when we're thinking of a star which has large length scales, the magnetic Reynolds number is typically very high, which implies that magnetic fields are more or less frozen in the plasma flows. And we couple that with the fact that the plasma beta parameter, which is the ratio of the gas pressure to the magnetic pressure in the convection zone of stars, is pretty high. That allows dynamics of plasmas to govern the evolution of magnetic fields, and more importantly, allows the channeling kinetic energy of the flows to magnetic energy. And this is really the crux of how a magnetic dynamo derives energy from convective flows in stellar convection zones. So what do we understand about the solar dynamo? What's the standard picture? Let's say the non-controversial standard picture of the dynamo mechanism. So we know that if you have a pre-existing poloidal component of the field, which is here on the left-hand meridional cut, differential rotation will stretch it and induct a toroidal component of the magnetic field, which is in the phi direction, and magnetic buoyancy of the toroidal flux tubes would allow these flux tubes to rise up and create sunspots, and Coriolis force would tilt the apex of these rising flux tubes to provide a tilt angle. It's also thought that helical turbulent convection during this rise process of the toroidal flux tubes can create a helicity out of which a traditional mean field alpha effect arises. So it's believed that the toroidal field then can contribute to the regeneration of the poloidal field through two different processes. One is the decay and dispersal, redistribution of flux of the small bipoles or dipoles within the regions that emerge tilted, or through the mean field dynamo alpha effect and recreate the poloidal fields. So this is how dynamo cycle runs. All right. However, the cycle doesn't really look like this, right? The sunspot cycle looks like this. There are fluctuations. And to understand predictability and our ability to be able to forecast whether the next cycle is going to look similar or dissimilar from the previous cycle, we really need to also understand what creates these fluctuations in the sunspot cycle and what contributes to the strength of sunspot cycles. So I will be quite motivated by observations here and try to constrain my path forward. And I would postulate that based on certain observations, it's pretty clear to us now, the variability in the amplitude of the polar field is reasonably explained by the Babcock-Lytton mechanism. You see a observational plot of the source term for the Babcock-Lytton mechanism derived from observations, which is here, the tilt times the area of sunspots versus the active region area that emerges in the next cycle. And you see a reasonably good linear correlation. This is an idea that was derived from Babcock and Layton, which is that the flux of tilted bipolar sunspot pairs, which is redistributed by surface flux transfer processes and flux cancellation across the equator, creates a net polar field at the end of the cycle. So observations support this scenario. Analytic theory based on Maxwell's equations support this scenario. And data-driven surface flux transport and dynamo models are also able to explain the solar cycle variability over century scale based on this mechanism alone. Now, having said that, we have fluctuations in the sunspot cycle. And how can fluctuations arise? So it is believed that during the rise of a buoyant magnetic flux tube from the convection zone base to the surface, this is interacting with turbulent convection. And this, if you're thinking of the mean field turbulent convection, mean field alpha effect, this can create fluctuations in the mean field alpha effect. It can also buffet the rising flux tubes and create a dispersion around the mean tilt angle that is expected from Joy's law, so that you can have variations from cycle to cycle. So these are some mechanisms that have been thought can introduce stochasticity in the dynamo mechanism. On top of that, we have nonlinearities in the cycle. So we are dealing with a system where there are Lorentz feedback, there's magnetic feedback on the internal as well as surface flows, and various people have looked at models exploring the influence of magnetic feedback. There is helicitic quenching at a more fundamental level, which has a catastrophic effect sometimes on the mean field alpha effect. There are nonlinearities due to time delay effects, which is a novel kind of nonlinearity, which also results in amplitude modulation of dynamo mechanism. There are dynamical buoyancy effects, where the buoyancy depends on the strength of the magnetic field, which is within the flux tube that is currently rising. And then there is magnetic feedback on the tilt angles of active region, which results in tilt quenching. And this has also been explored both through thin flux tube simulations as well as observations. What is important to note here, that nonlinear feedback mechanism is especially important in supercritical regimes. And why is this? Because studies in the field of nonlinear dynamics shows us that when you have stochastic fluctuations or random kicks in a highly supercritical regime, this becomes particularly important because the impact of those are really felt over long time scales and they add up. And this gives rise to a background modulation, which is over and beyond the stochastic perturbations in our dynamic system. So this is a nice plot that I like to show. This is really a lesson in nonlinear dynamics that Paul derived using a dynamo model, where what was done was the forcing term or the dynamo number was increased, and then nature of the dynamo was studied. On the y-axis, what you see is the amplitude. What is the square of the amplitude? And what you see here is that first you have pretty regular, singly periodic transport cycles. Then there is a period doubling bifurcation, where you have two different pathways for the cycle to take. This is followed by another period doubling bifurcation, and then the cycles also become somewhat irregular. And then at very high forcing or high dynamo numbers, at very highly supercritical regime, it looks like the dynamo has become quite chaotic. So let's then get back and ask ourselves the question, if the solar dynamo is really chaotic, prediction is possible. So Paul Bushby and Steve looked at this question, and what they did was they did a dynamo simulation of a nonlinear dynamo, slightly different initial conditions, and they found that dynamo solutions converge after multiple cycles, and they diverge after multiple cycles, and this start diverging like whatever. They interpret this as predictions of solar dynamo based on solar dynamo mechanism of the solar cycle are not possible. Now, this is something that was well known for quite a while. I have a snapshot here from a famous paper by Edward Lorenz, who was looking at convection in the context of weather. And he concluded that due to the inevitable inaccuracy and incompleteness of weather observations, implying initial conditions, precise, very long-range forecasting would seem to be non-existent. And this is perhaps true for the solar dynamo mechanism as well. So let us then reframe the question and ask ourselves, is short-term predictions, not necessarily up to infinite timescale or many solar cycles, but is short-term prediction possible for the solar dynamo mechanism? If yes, what is the predictive window or predictive memory in the system that would allow you to predict the sunspot cycle up to a certain time in advance? So this is a paradigm for solar cycle predictions that I've been exploring, and I would like to postulate looking at the underlying physics. So if you look at the dynamo equations for the evolution of the toroidal field and the toroidal field, much of the terms are flux transport terms, which you can think of as deterministic. Okay? But they introduce a certain time delay in the system because it takes a finite time to move around flux between various parts of the convection zone. If you look at the toroidal source, which is the stretching of the toroidal field with differential rotation, it's also fairly deterministic. The feedback there is so small that Ortholon oscillation that you see is only a few percent of the overall differential. If you look at the poloidal source, that is however stochastic, and you see this, and this is because of the random buffeting of rising flux tubes and the tilt angle fluctuations that you see, which is observed. Okay. This term, and in fact its time variation, luckily, the radial component of it is observed on the solar surface in the radial component of the magnetic field distribution that you see, right? Therefore, there is a means to bypass this equation and feed in that observation, therefore, which includes the stochasticity and incorporate that in the equation for the toroidal component here, such that you can solve for this equation and generate the next transport cycle amplitude. This is something that was postulated by Shatton et al. In 1978. I explored this as a proof of concept to look at whether one can vary the poloidal source randomly and that this creates predictable variation in the toroidal field. And I had an abstract in 2002 about it, but I never went ahead and published it. But people followed it up. Now, what's the spirit here? The spirit here is by data assimilation and by replacing this term here with observations, what you're really doing is reducing the system philosophically to a sort of time delay system where you're predicting the sunspot cycle for the next cycle, which is the toroidal field, based on observations of the poloidal component with a certain time delay or predictive memory T0, which is introduced by the finite time taken by flux transport processes. The predictive memory lasts roughly over the time scale T0, which is the memory in the system, and not beyond, and therefore predictions are possible roughly on the order of this dynamical memory in the system. So that's the paradigm that has evolved over the past decade or so. Now, this implies we should have a very good handle on what are the different time scales for transporting flux. We know that meridional circulation takes roughly about decades to close the loop and travel around convection zone. Turbulent diffusion, which is just, takes the poloidal field down towards and spreads it out in all direction, also takes it down to the convection zone base, takes about 14 years to do so. Turbulent pumping achieves this much faster on the time scale of something like 3 to 4 years. The memory is really determined by the interplay of all these processes and is particularly governed by the fastest of this process, because in its stochasticity in the poloidal field generation, quickly taken away into the generating layer for the toroidal field, and therefore will have its imprint at a time scale corresponding to the fastest time scale. And this has been explored also, that the idea of this memory has been explored in various dynamo models over the last couple of decades. So let me now tell you the impact of this memory system. And if you look at what governs this memory, if you do a dynamo simulation which is advection dominated, with meridional circulation playing an important role with very long-term memory, then the simulations show that there seems to be correlation between the poloidal field strength of cycle n with the toroidal field strength of cycle n+1, as well as the subsequent cycles with some decreasing correlation. Whereas in the diffusion-dominated regime, where you have much faster transport of the poloidal field to the base of the convection zone, and therefore shorter memory, the memory persists for only one cycle. Now, interestingly, if you take the advection-dominated dynamo model and introduce turbulent pumping, which sort of short circuits this whole process of advection, then the memory also reduces to only one cycle. This implies that the sunspot cycle probably has a dynamical memory not extending beyond one sunspot cycle, and the polar field at the minimum of a cycle contributes to the strength of the next sunspot cycle, not beyond. All right, so let's look at what observations tell us about this sort of theory of predictability that we're trying to postulate. If you look at long-term observations of polar faculae, which is a proxy for the poloidal field, and correlate them with the amplitude of subsequent cycles, you get some interesting results. First of all, you see that the sunspot cycle amplitude of a particular cycle does not correlate with the poloidal field at the minimum of that cycle itself, which means that this deterministic link is broken. And this is because the poloidal field generation mechanism is stochastic, as we have argued, right? If you look at correlation between the polar field at minimum and the next sunspot cycle, there is a strong correlation, which means this process, in fact, is to some extent deterministic. And one can make predictions the next sunspot cycle based on the strength of the poloidal field at minimum. This agrees with the theory of solar cycle predictability paradigm that we are arguing about. All right. Based on this,
Dibyendu, 5 more minutes.
Yeah. So based on this, we have the understanding that predictions are possible only at the minimum of cycle. Then we asked ourselves the questions a few years back. Can we extend the predictive window? Is there a way to extend the predictive window cycles even beyond, right? How can we do that? So, of course, surface flux transport models have been there for quite a while. And we thought, okay, fine, we can utilize a surface flux transport model and predict the sunspot cycle poloidal field at the minimum of the cycle first, and then use that in a dynamo model, predict the next sunspot cycle, which will then extend the predictive window beyond the 5 years that you get typically for sitting at the solar minimum, right? So what we did was we utilized a 2D kinematic dynamo model, the output from a 2D kinematic surface flux transport model, and incorporated that into a 2D kinematic dynamo model to extend the forecasting window and predict sunspot cycle 25. Before we did that, we actually did a century scale simulation. The way we did that was to first incorporate the typical observed statistics of sunspot latitudes and tilts of bipolar magnetic regions in the surface flux transport model, and simulated that over century scale. And what you see here is that simulation, the thick lines are the simulation, background thinner lines, the polar faculae observations, which shows how the simulations matches with the observations. And then for the last cycle, we used a synthetic sunspot input for the declining phase, for the last 3-4 years of the declining phase. But then also introduced an ensemble forecast by varying these input parameters to create an ensemble forecast of the poloidal field strength at the minimum. And subsequently, what we did was we took a dynamo model, and then the dynamo model was initialized and then forced every solar minimum by the output of the surface flux transport model. Based on this, we produced the first century scale data-driven surface flux transport plus dynamo simulations. And the solid red lines is the result of our simulation, and the black curve is the observations. You'll see that we have matched past cycles pretty well, except cycle 19. And this is something that we are worrying about now, but I'll not go into that. It is particularly important to note that no model parameters was fine-tuned after we initialized dynamo model. The only way it was perturbed was by incorporating the surface flux transport output at the minimum of the cycle. And based on this, we predict that sunspot cycle 25 is going to be a weak cycle with a range that is just slightly weaker than the current cycle to somewhat stronger than the current cycle. And we estimate the time of peak to be between 2023 to 2025. Now, let me come back to this question. And this is something that I critically assessed and review in a recent, well, it is not yet out. It's been accepted in solar physics, a review paper on progress in solar cycle predictions. So this was the state of predictions for solar cycle 24, utilizing different kind of techniques. Dashed line here is the actually observed strength of cycle 2024. All right, and you see this is all over the place. Has the situation changed? This is sunspot cycle 25 predictions using a diversity of techniques. And this dashed line again is just the previous cycle, cycle 24 strength for comparison. And you see, using this different kind of techniques, we still get wide disagreement for sunspot cycle 25. However, if you look at the physical model-based predictions based on the backpropagation mechanism, various papers, one by group of Paul Charbonneau, Labonville et al., then Upton and David Hathaway, then by us, Bhumika Nundy and Ji Jiang. Now, within the uncertainties of this model, they all converge, and they indicate that cycle 25 is going to be a reasonably weak cycle, similar, or maybe slightly stronger or weaker than cycle 24. All right, with that, I come to the last cycle, last slide. And I pose this question at the beginning of the talk. Is it possible to predict the solar cycle? I hope I've convinced you, yes, it is possible in the short term over one cycle. If yes, what is the best proxy for prediction? Best proxy is the polar field or the flux that is observed at near minimum. Do we understand why one dynamo prediction matched past cycles quite well, but not cycle 24 wrong, and why the two dynamo-based predictions of cycle 24 disagreed? Yes, we know that because one of them was working on an advection-dominated regime, whereas another one was working on a diffusion-dominated regime, which created different memories in systems, as well as input files of driving by observations was different in these two models. What can we predict for the future cycle and how accurately? So we can predict the transport cycle amplitude and the timing to some extent. And the assessment of accuracy may be made based on statistical possibilities or ensemble forecast, which provides a range of possibilities. And it's important to consider that range and not the particular number, which is not the right thing in my mind. Now, how early can we predict? Well, if you just base it on observations, you can predict probably at minimum, but if you use SFT plus dynamo models, you can extend this predictive window to almost. What is the early outlook for transport cycle 25? Well, it's going to be a weak cycle, but there is going to be no monomer minimum, and it's not going to be an insignificant cycle. That's the current consensus. With that, I will end. Thank you.
Thank you, Deepen. Time for a couple of questions. Vidya, can you ask your question now?
Yeah. So I have a quick comment first. So one thing is that I think discussing the physics-based or the model-based prediction, I think you missed this Choudhury and Hajra prediction. I mean,
I didn't miss it. It's here. You didn't see this plot properly.
Okay. I was seeing the last one. I was seeing this. Okay. So there's another thing that. So you're discussing the result of the polar field memory based on the polar faculae data.
Right.
So there I would like to make a comment that polar faculae data is available only for like 10 cycle, and during that time the solar cycle was relatively strong. So so it just covered only a small subset of the whole solar cycle window. So
that is not true. Over the last 10 cycles, you have weak cycles, which is here. You see weak cycles here. You see weak cycles here.
What I mean is that, like, at least from this, like your low order dynamo model and also the flux transport dynamo model, what we find is that if you take a small portion, okay, then you get a different result. But if you include the like a extended grand minima like phase, like the Dalton minima and the Monday minima like that we have in the sun, then we get actually different memory of the polar field. Like
absolutely. So everything that I said is not pertaining to anywhere where minima, because at minimum, at grand minima, at least I believe the nature of the dynamo was completely different. And this is not a backward Newton dynamo anymore during the minima. So yeah, I mean, physics will change if you're considering the minima.
Well, so just one more thing, that is, as you said that, okay, it will not be a Babcock-Leighton type dynamo. That's fine. That may be true. But this memory of this polar field is very generic. Like even if you have any type of like alpha omega type dynamo model, as long as the polar field is feed back to the toroidal field through differential rotation, as long as there is some transport mechanism, then the poloidal field must be correlated with the toroidal field, and also there may be multiple correlation depending on the properties.
Yeah, Vidya, that is known for like ever, right? I mean, that the poloidal field would translate to the toroidal field is something that is the basis of alpha omega dynamos. I'm not talking about that. I'm talking about if you introduce perturbations in the poloidal field, would it actually wipe off that memory even before one cycle? In the sense, would that remove correlation between the polar field at minimum of the next transport cycle, where you don't have a perfect correlation? I believe it can if you have strong stochasticity and the flux transport time scale is much smaller than the time scale of the solar cycle. The other thing is, would this memory last over multiple cycles because of interactions of multiple field belts? Yes, it will last if you have advection dominated regimes where multiple field belts are interacting. these are important physics that you cannot, that is over and beyond the typical idea that you have from the alpha omega diagram.
Maybe we can move on to like one more quick question. Arnab, would you like to ask a question?
Okay, sure. I would like to make a comment on the basis of the physics of the Hajran Choudhury paper, which Bidya mentioned. So in your otherwise,
here, I guess.
Okay, so in your otherwise comprehensive review, you have omitted one effect, which I personally think very important, that we have indirect evidence that at sometimes in the past, especially in 19th century, there were large variations of meridional circulation. And we have from dynamo models tell us that fluctuations of meridional circulation also can have effect on what will be the strength of the cycle. So I think in the last few decades, meridional circulation has been fairly stable. So if you are just predicting cycle 25, then probably it is okay that if you do not consider these variations of meridional circulation. But I think we may again enter a phase like 19th century when there are large fluctuations in meridional circulation. So if you want to look beyond cycle 25 and want to address the broad question of how to predict solar cycles in general, then I think the effect of variations of meridional circulation also should be taken into account. And that is what we discussed in this Hajran Choudhury paper. So I thought, as I said, that out of the formula which we got, I think our prediction for cycle 25 is very similar to predictions of your prediction and other predictions of dynamo-based prediction. But we should keep in mind this possibility that there may be more fluctuations in meridional circulation, and that may make things different.
I appreciate that comment in the sense that I have myself worked with it, and I know from the premise of the dynamo models that we construct, flux transport models, yes, variations in meridional circulation can do lots of things. It can even trigger minima. But I would like you to look at this plot. I'll not answer your question today because we are working on it. We did not touch the meridional circulation. However, we got the amplitude of the cycles as well as the timing right. I will say no more, but there is great physics in there, why this is happening. So I based on this, our previous simulation, I would strongly think there is something else that we have been missing here. And this is the physics we are now working to unveil. How did we get the timings right? We didn't tweak anything. Let's think about that. I will not say any more.
Okay, sure. I look forward to your results.
Yeah.
Okay, and thank you, Dipendu, for the interesting talk. We shall now move on to the next talk by Bidya Vinakara from ITBHU on nonlinearities for the saturation of magnetic field in the sun. Bidya, I shall be giving you a reminder after 10 minutes.
Okay, yeah. So now you should be able to see my full screen.
Yes.
Okay, very good. Okay. So first of all, let me thank the organizer for giving me this opportunity to present my work here. So as the title says, I'll discuss nonlinearities for the saturation of magnetic field in the sun. Okay, so I begin by showing this plot of sunspot number for last 400 years. So the important point that I would like to focus here is that although the amplitude of this solar cycle has significant variation from one cycle to other, the overall amplitude of the solar cycle does not grow all the time. At least this is true in the past. Okay, so there must be a mechanism, okay, in the dynamo process, okay, which tries to limit the growth of the magnetic field in the sun. Okay, so this is the popular dynamo quenching. Okay, so dynamo quenching is a very vast and very popular topic in the dynamo. Okay, but I will discuss this dynamo quenching in this solar cycle aspect. Okay, so now I mean I don't have to give much details of the solar dynamo because already there are two talks which nicely cover the different aspects of the dynamo theories. So I'll straight away focus to the so-called current most supported model of the solar dynamo, which is the Babcock-Layton type dynamo model. Okay, so the picture is very simple. It's the oscillation between two type of field. The poloidal give toroidal through differential rotation in the solar convection zone. And then toroidal field give rise to this bipolar magnetic region, or we loosely call sunspot. And then decay and dispersal of sunspot give the poloidal magnetic field. Okay, so this is the broad picture. Okay, it may not be the complete picture. Okay, but at least I'll focus my talk based on this Babcock-Layton type dynamo model. Okay, and as Dibyendu said that there are some support from observation. Okay, behind this type of dynamo loop in the sun. Okay, so now in this dynamo loop, what could be the mechanism for limiting the magnetic field growth in the sun? Okay. So I'll take one by one of these processes from this dynamo loop, and I'll discuss like which process could have nonlinearity to provide the source for limiting the growth of magnetic field. Okay, so the major component in this dynamo loop is the differential rotation. Okay. Differential rotation give rise to a toroidal field from poloidal field, and it is measured for last like several decades. And from those observations, we know that there is a very tiny variation with the solar cycle, which is called the torsional oscillation. So other than that, there is no variation in the differential rotation. So possibly this differential rotation is not the source for limiting this growth of the magnetic field in the sun. Okay. Next, we have the meridional circulation, which at least in this type of dynamo model play a very important role. And we have a lot of observation of this meridional flow in the on the surface of the sun for many years, but we have a lot of divergence in the result and also in the deep convection zone. So we cannot say anything conclusive whether this meridional circulation can be the source for limiting the growth of magnetic field. Okay, next we have turbulent transport such as turbulent diffusivity, magnetic pumping, etc. Okay, so certainly this can introduce nonlinearity in the dynamo process, but possibly they do not limit the growth of magnetic field. Next, we have this Babcock-Layton process. Okay, now this is a process through which the poloidal field is produced largely in the sun. Okay, now I'd like to mention that this is not like this helical alpha effect. Okay, that we know in the traditional Millfield dynamo model. So it does not suffer this catastrophic quenching that we know so popularly called the alpha quenching, because this is a non-local process. Okay, so the toroidal field rise due to magnetic buoyancy, and during its rise, the Coriolis force possibly give rise to this tilt. Okay, now and then this poloidal loop that actually get disconnect from this parent toroidal field. Okay, so so basically there is no linkage between this original toroidal field and this poloidal loop. So there is no this alpha quenching, okay, in this process. Okay. Despite of that, there is, I mean, there are some mechanism, okay, which possibly can have some non-linearity. For example, tilt of bipolar magnetic region has some magnetic field dependent. Okay, that we have seen based on observation, and there is some strong theory behind this. Okay, so Vibhuti Jha will discuss the possible quenching of tilt, okay, in the dynamo process. Okay? And then there is other mechanisms like inflow around BMR can have some magnetic field dependence, and there is another important process is called the latitudinal variation of bipolar magnetic region. This is popularly called the latitude quenching that has been recently realized. So my talk is focused will be discussing this aspect, this latitudinal variation of sunspot, which is the latitude latitude quenching. Okay, so this was this idea was given by Jiang, and then almost at the same time I was doing this dynamo calculation based on this idea. So these two paper actually discuss this latitude quenching. Okay, so the idea is based on this observation fact. Okay, so you see this latitudinal distribution of sunspot, which is popularly known as the butterfly diagram. So you see that around at the beginning of the cycle, sunspots start appearing from about 30-degree latitude, and then they migrate towards the equator. So this is the equatorial migration of sunspot. Okay, and the interesting point to note here that this latitudinal position of sunspot are not same. So for example, like when you have a strong cycle, they start producing BMR and sunspot somewhere at higher latitude. Okay, but the weak cycle, they give rise to sunspot at lower latitude. Okay, so this feature was nicely demonstrated by Solanki et al. In 2008. So what they did, they computed the mean latitude of the sunspot and plot as a function of the cycle strength. Cycle strength is measured as the total area of the sunspot. Okay, so you see a positive correlation, and this was again reanalyzed based on varieties of data and also using dynamo model. So what we generally find is that the strong cycle has the mean latitude of sunspot is higher. Okay, weak cycle has lower mean latitude. Okay, so there's a positive correlation. Okay, on the other hand, there's another property that came from the surface transport model. Okay, so this this surface transport model, at least in last few years, has been producing many interesting result, and they are very good agreement with the observation. So one result from this SFT model is that if BMR appears at low latitude, then they contribute to the polar field at highest. Okay, so the BMR appearing at higher latitude, like 30-degree and 40-degree latitude, they give almost no polar field. Okay. Now the question is this result true in dynamo model? Okay, if this result is true, then it has a very interesting consequence. Okay, so to explain this, consider a cycle which is strong. Suppose a solar cycle becomes strong. Okay, then we have seen in the observation the strong cycle give BMR and sunspot at high latitude. Okay, and if you have a BMR at high latitude, then from this SFT model we see that it gives weak polar field. Weak polar field means the next cycle toroidal field will be weak, so the next cycle will be weak. So indefinite growth of the cycle is now halt. Okay, so this is the dynamo quenching in this model. Okay,
so we have 2 more minutes.
Yeah, so my job is to capture this idea. Okay, so this is the whole message. Okay, so I capture this idea in a 3D dynamo model. It's called stable dynamo model. So this stable stands for surface transport and Babcock-Leighton dynamo model. The model was originally developed by Mark Mies, and then later I did some contribution in it. So it's essentially a 2D kinematic type dynamo model, but this BMR emergence, decay, and dispersal are improved in this model. Okay, so it solved this induction equation, okay, in the whole convection zone, and it works at reasonably high diffusivity with some magnetic pumping. Okay, so there are some technical details. So the important part is that it produces BMR. Okay, once the toroidal field at the base of the convection exceed a certain value. Okay. Okay, so so the magnetic field has to be greater than this BT, the threshold value. Okay, where this BT is given by this exponential factor. Okay, so it increases as you go towards the pole. Okay, exponentially. Okay. And also the time difference between two BMR has to be larger than a certain value delta that is obtained from log normal distribution. Okay, so then other properties of BMR taken from observation. Okay, Okay, just to show that that this BMR appearing high latitude give less polar field. So I'll show two clean experiment where we have deposited BMR at two different latitude. Here you have BMR at 2 degree latitude. Here you have BMR at 25 degree latitude. Okay, so there is no any imposed magnetic field. Just two BMR are deposited at two different latitude in these two cases. Okay, and tilt is taken from Joyce law. Okay, tilt is equal to some constant and then the sign of lambda, the sign of latitude. Okay, so in this model, all the ingredient are given like turbulent diffusion, meridional circulation, and the differential rotation. All these basic ingredients are given. So all this allow this BMR to decay and disperse and produce this this poloidal magnetic field. But to note here that this BMR which appear at like 2 degree latitude give much stronger field. Okay. So I have done systematic analysis. What I find in general is that if BMR appear at high latitude like 25 degree and 45 degree here, you see they contribute to a much weak polar field in comparison to BMR which appear at somewhat lower latitude like 5 degree, 10 degree. Okay, so this is in somewhat agreement with the SFT model, but not completely. And I'd like to mention that Hajra et al. Did not find this behavior because they miss one component, which is the turbulent pumping. Okay, but we found that features. Okay, so once that features is captured properly, then this model produce a stable magnetic cycle. Magnetic field, as you see here, does not grow indefinitely. Okay, we have done many simulation. Okay, so this is a simulation. We have also included scatter in the BMR tilt. Okay, and we see that there is no stable cycle. There's no imposed nonlinearity. Okay, so this is the features that we see, that mean latitude as a function of cycle strength. Okay, so that we have seen in the observation. Okay, so here are my three conclusions. Okay, so first is that latitudinal quenching as proposed by Jiang alone halt the growth of the magnetic field in our dynamo model. However, when the dynamo is too much supercritical, that means if you are at much above the dynamo transition, then latitudinal quenching alone cannot limit the growth of the magnetic field in our model. And the tilt quenching that I did not discuss, but Vibhuti Jha will discuss, is an additional candidate for the saturation of magnetic field in the sun. Okay, I'll stop here. Thank you.
Thank you, Vidya. So time for a couple of quick questions. Sushant, would you want to ask a question?
Sorry, I'd raised my hand during the Bendu's talk. Over here.
Any other questions for Vidya? Okay. If not, then we just so one quick announcement from the SOC before the last talk. So we'll be taking a conference photo by means of a screenshot of the gallery view after end of the last talk. So we request all of you to keep your videos on after the next talk. It's over. So with that, I invite Hannah Shunker from Newcastle to give the talk on closing of the solar cycle, emerging active regions.
Hannah, you're muted.
Hi, you are muted. Oh, okay.
Can you hear me now?
Yes, yes.
Yes.
Thank you again to the organizers for organizing this meeting across many time zones. What you are seeing here are images from the SDO satellite of the line of sight magnetic field. And what you will see in the middle here is an active region emerging.
Your screen is not sharing.
You can hear me?
We can
Yeah, we don't see your slides, Hannah.
We can hear you, but we see you. Your slides are not on.
Yeah, now it's fine.
Yeah, now it's
Okay. Now what you are looking at are line of sight observations of the magnetic field taken by the SDO satellite. What you can see here is an emerging active region emerging onto the surface of the sun. These are an extremely important component of the solar dynamo because it is what converts the toroidal field to the boloidal field. And so understanding how active regions form will give us some idea of where they are coming from and where the dynamo sits inside the sun. The work I will review in this talk covers the last 5 years or so, which has been done with my colleagues in Germany and the US. So active regions have been observed for a very long time in the continuum of the sun, and they're characterized by sunspots. And we now know that these sunspots are locations of strong concentrated magnetic fields in bipolar configurations, which then, where the magnetic field then extends out into the atmosphere in these beautiful loop-like structures. But we don't understand how they form. Active regions are also very important in the fact that they just define the solar cycle. That's how we define the solar cycle. Here we have, as a function of time from the mid-70s up until today, as a function of latitude, the line of sight magnetic, longitudinally averaged line of sight magnetic field. We see the butterfly diagram, as has already been shown a few times. We see that the general strength of the magnetic field on the sun increases and decreases with an 11-year period. And if you look at the polarities at the poles, you see that the polarities change every 11 years, giving a 22-year dynamo cycle. So these active regions are very important in this conversion of the field and the dynamo process. A very simple way of thinking how the dynamo works is we begin with a boloidal field, which is then wrapped around the sun by the differential rotation, which is faster at the equator than at the poles. This then gives us the toroidal field with opposite polarities in each hemisphere. This toroidal field, which is below the surface, rises towards the surface, pierces the surface, and this is when we observe the active regions. The process continues with the flux being transported to the poles, return to the interior, where we then form a boloidal field, again, now with the opposite polarity, and the cycle starts again. So what I think is a key component into understanding what is happening in the dynamo here and where this dynamo is located inside the sun is to understand how this happens. The active regions are the closest we can get to a direct measurement of the magnetic field inside the sun. So how do active regions form? This will help us close that dynamo cycle. I'm separating these into two camps, which is very similar to how Matthias separated these yesterday. One is the passive models and one are the active models. The passive models is an example shown here where the magnetic field in the dynamo is generated within the convection itself. So the magnetic field is twisted and sheared by the convection. And here we can see the general opposite polarities in each hemisphere that's generated by the convection. On the other hand, here we have what I call an active emergence or an active formation of an active region. Here, the thin flux tube model is located below the convection zone. It then rises up through the convection zone, completely ignoring convection. So this is what I'm calling an active emergence, ignoring convection. So we can observe, if we can look at these active regions as they emerge, then we can try and constrain the physics and point towards whether we think active regions are more, they form in a more active sense or in a more passive sense. So we do have one tool to see below the surface, and that is helioseismology. And various authors have attempted to image the subsurface before active regions emerge with various results. So one of the ideas is that as this thin flux tube model rises towards the surface here, because it's rising through less dense material, it gets less dense as it gets higher, material flows down the legs and there are flows in the tube itself. Here we are seeing a map of the prograde flows generated by a rising flux tube. So here is longitude, here is height below the surface, and this blue area here indicates a retrograde flow. So prograde is always in this talk anyway, towards the right. A retrograde flow near the peak of the flux tube at about 50 megameters below the surface. These lines here indicate the ray paths of waves that helioseismology can use to try and detect these flows. And there was an estimate that to get a sufficient signal to noise to be able to measure 100 meter per second flows at those depths, we would need about 100 active regions to average over to be able to measure that with helioseismology. So these authors, and there was a series of 3 papers, were published with the goal to do this. But unfortunately, no flows were detected. But they only looked up to 20 megameters below the surface and up to 1 day before emergence. And as you may note here, is that these thin flux tube models stop about 20 megameters below the surface. So perhaps we should be looking deeper and further back in time. And now we have SDO. I should mention that that previous result was done using SOHO observations and GONG observations. But now we have SDO, which allows us to do statistical studies of emergence, because this is only possible with monitoring campaigns. Since we don't know where an active region is going to emerge, it's very difficult to point our telescope at a region of the sun and wait for something to emerge. This would be a very difficult thing to capture. So we are in a unique position now with intensity observations, line of sight magnetic field observations, as well as the Doppler velocities to use helioseismology. So we have these high duty cycle, high resolution observations. I would also like to particularly point out that we now have the magnetic field. Prior studies were typically of intensity continuum, and they were case studies because it's very hard to capture an emergence if we don't know where it's going to happen. But now we can do this for many active regions. In addition, we have these realistic quantitative 3D MHD simulations, as Matthias showed yesterday, which are just absolutely beautiful, that we can directly compare to our observations. So we're in a good place to understand this problem. So from SDO, we put together the Helioseismic Emerging Active Regions Survey. This consists of 185 clean emerging active regions. Clean meaning that they emerge into regions that do not have existing strong magnetic field, in addition to a corresponding control region for each of these active regions. In the control regions, no emergence occurs. So we have the intensity, we have the line of sight magnetic field, and we have the surface velocities, including travel times for the waves, with turning points up to 70 megameters below the surface. We tracked these active regions across the sun up to 7 days before emergence and post-emergence, depending on where on the disk they emerged. And all this data was computed by and stored at the German Data Center for SDO at the MPS. So now we have a sample of active regions where we can try and understand the common physics behind their emergence. So before we can understand what makes an active region small, what makes an active region long-lived, we can understand their common properties. Here is an example of the data in the data series. On the left, you're looking at active region 11209, which is at the center of the field and is rather weak. It emerges, it develops, and then it decays. You will also notice some emergences occurring in the field in the lower areas here. These are not included in our sample because these emergences occur in regions of strong magnetic field. But it gives you an example of other kind of emergences that can happen. On the right side, we are looking at active region 11158, which is the strongest active region in our sample. And this emergence is a lot more complicated. It's sort of a double emergence where the bipoles emerge and then they reorganize themselves into the classical bipolar structure. So this just shows the range of active regions. An active region is defined by its darkening in the continuum. So an active region has to at least reach that magnetic field strength. In the rest of this talk, we have reversed all active regions in the Southern Hemisphere, including active region 11158. So if you see it looking a bit different, that's why. We reverse the latitude and we times the magnetic field by -1. So we treat all of the active regions as if they're in the Northern Hemisphere. And I'd also like to emphasize that the way we define the emergence time, there is a small amount of flux already present in our observations at the emergence time. So if we just zoom into this area closer in, we show a summary of our observations. The gray scale indicates diverging and converging field at the surface. The arrows indicate the direction of the field. The blue and red colors are the line of sight magnetic field. And the contours you see appear represent roughly the umbra and penumbra from the continuum. So this is the data we have in our data set. The dominant scale of convection you see at the surface is supergranulation. So just keep that in mind, these diverging cells you see. So our goal is to constrain the physics guiding active region formation, which will help us understand where active regions originate and hopefully where the dynamo lies. Is it deep below the convection zone or within the convection zone itself? I'm going to address 3 things today. One is the rise speed of active regions. Matthias spoke about this yesterday, so I'll go fairly quickly over that. The second is looking at the average surface flows. What scales of convection are important for active region formation? And the third is Joy's law. And as has been highlighted in previous 2 talks, I was very happy to see, this is a crucial part of some dynamo models, and we would really like to understand what is causing this. So the rise speed of the flux tube. In the thin flux tube models, once the thin flux tube gets towards the surface, it is rising at about 500 meters per second. But like I said, these models stop about 20 megameters below the surface, and that's when convection becomes important. So with these Murm simulations, in the bottom boundary, a flux tube was pushed through the bottom boundary with a particular upward rise speed. And we can see here these beautiful observations, the simulations of the intensity and the line of sight magnetic field forming the classical bipolar structure and really looking very similar to our observations. So we are able to quantitatively compare these simulations to our observations. So with an upward rise speed of 500 meters per second, at the time of emergence, as we define it, we see an enormous outflow at the surface. Here we are looking at the time of emergence. We have a diverging flow in red and a converging flow in blue. The arrows indicate the direction of the field. The gray are contours of magnetic field strength, maybe 10 Gauss or something like that. This number indicates the upward rise speed of the tube. If we compare that to what we see in the observations, so this is active region 115A, the strongest active region in our sample, we do not see these strong outflows. And in fact, for any of the active regions in our sample, we do not see this. But if we change the upward rise speed to about 70 meters per second, we get flows that are on the order of what we observe in our sample. And 70 meters per second is on the order of the local convective velocities near the surface. So this seems to indicate that active regions are not barging through the convection zone and popping through the surface. They're coming up much more passively than the thin flux tube model may suggest. So let's move towards looking at the average surface flows. Here you are looking at the average surface flows over many active regions. Again, blue is converging, red is diverging flows. The black arrows show the direction of the flow at the surface. This is 35 hours before emergence, and where the active region emerges is indicated by this white spot at the middle. So at 35 hours, we see a pattern like this. 24 hours before, we see a map that looks like this. 13 hours before, we have this very strong east-west aligned converging flow. And once emergence occurs, we see flux at the surface, as I mentioned earlier. And we see the continuation, but not as strong, of this east-west flow, this converging flow here. So it seems that active regions prefer to emerge on the prograde side of an east-west aligned converging flow lane. And this made us think that perhaps this has something to do with the convection, so a converging flow lane. So we assumed a very simple model, and using our control regions, so this is exactly what you saw before on the left, using our control regions on the right, we identified east-west aligned converging flows in our control sample, not where emergence occurs, and averaged them with the location of a synthetic emergence at the prograde end. And we get a pattern that is not dissimilar to what we see here. So this is a very simple model, but it suggests that perhaps active regions prefer to emerge in these inflow lanes between supergranules when they are east-west aligned. A very brief advertisement here from some hot off the press results. Here you are looking at LCT surface flows averaged over 12 hours. Previously, they were 6 hours. Now we have 12 hours. The pixel size is also larger. There's 4 megameters per pixel compared to 1.4 in the previous data. So just be aware of that. These are slightly different flows. But here we are looking at the average surface flows as a function of flux. So here we have low flux regions, and here we have very high flux regions. And this is at the time 18 hours before emergence. And we see the familiar inflows. Now we go to 18 hours after emergence. And we start to see here, and I'm going to zoom into this, a north-south inflow. The red and the black, red and the blue indicates the line of sight magnetic field. So these are averaged over 45, 46, 45, 46 different active regions in the sample. So if we zoom in, we see that there's a north-south converging flow happening here. If we go to 18 hours, 1 day after that, we start to see the onset of this flow here. You will also notice that there is this large outflow. This is the moat flow that there were some questions about yesterday. And if we go again forward in time and look at the next flux sample, we see the north-south flows start to set in.
And now we have 5 more.
5 minutes.
More. Yeah.
And for the last sample, we see the inflow set in here. So this is by my student Niels Gottschling. So he has analyzed the larger scale flows and has noticed that the north-south inflows, the onset time is related to the maximum flux of the active region, and most importantly, the lifetime. We found no dependence on latitude. So it's not clear whether the active region is driving the flows or the flows are driving the decay of the active region, and our sample is not designed to analyze decay. But this is a really interesting result that we want to pursue to understand the further evolution of active regions. So coming to my last point is Joy's law, which is very important for many dynamo models. So as I said, crucial part of dynamo models, but it is a statistical feature. It is not a rule. Looking at the line of sight magnetic field of many active region bipole pairs, at any time, you will get various inclinations for them. But in principle, on average, we have higher inclinations further from the equator than closer to the equator. In the thin flux tube model, the idea is that these east-west flows, as they rise, have the Coriolis force operating on these flows, which tilts them. And so they emerge with Joy's law. So we want to measure the location of the polarities. Traditionally, again, I want to emphasize this has been done in white light, so continuum images of sunspots. And traditionally has been measured as a function of separation between the polarities and the inclination and the tilt angle. These were also often case studies. What we are doing is we are measuring the east-west separation and the north-south separation independently. This may seem obvious to do, it just simply hasn't been done before. So we are looking at the east-west and north-south separation and tilt angle. And in terms of the physics, if we think this is the Coriolis force operating, then this should be an important component to separate these two out. So this is the average motion of the polarities as a function of time. Here we have the leading polarity and the following polarity. Time moves away from the central axis. Here is a function of longitude. And here we have centered all of the active regions. This is poleward and this is equatorward. The first thing you can see is that they emerge roughly east-west aligned. This has been suggested before, but we have statistically constrained this here. The tilt angle increases with time. So this does not agree with traditional thin flux tube theory. They emerge east-west aligned and the tilt angle and Joy's law comes in over the first 2 days. We have defined 2 phases of emergence. Each of these points is about 6 hours separated in time. So you see that the polarities move apart faster, and towards the end, they have stopped moving apart. So this purple shaded area here is the first phase. And here, the separation speed increases. After this and outside this area, the separation speed starts to decrease before stopping at some point. The east-west separation, because we've separated this out now, is dependent on flux. Larger active regions separate more than lower flux active regions. Now, this was known as a function of separation, but had not been broken down into the east, west, and north, south. So the east-west separation is dependent on flux, but the north-south separation is not. As a function of sign latitude, here is the east-west separation at the time of emergence. It is about 20 megameters apart. The bipoles are about 20 megameters apart. 2 days after emergence, they are about 45 megameters apart. And you'll see that the larger flux active regions, the larger circles, are above the line, and the smaller circles are below the line. So this is a flux-dependent phenomenon in the east-west direction. In the north-south direction, they emerge very close to being east-west aligned. But after 2 days, we start to see that there is a latitudinal dependence. And this translates to the tilt angle. The tilt angle actually is on average -5 degrees, but within the uncertainties, this includes 0. And 2 days later, we start to see what we think, what is close to Joy's law. For example, as measured by Wang and Shili, they measure a relationship like this. So it takes about 2 days for Joy's law to set in. Here I've just summarized those results I talked about. The one thing I would like to add is that the north-south separation is dependent on latitude, not flux, and appears 2 days after emergence. And we also looked at this separation speed as a function of latitude, and it has a latitudinal dependence. So at the time of emergence, the polarities, the active regions are imbued with some north-south speed when we observe them. So our goal was to constrain the physics guiding active region formation, which will lead us to understand where the dynamo lies or where the dynamo is coming from. I presented you with 3 results. We have a series of papers using this data set, and I encourage you to have a look if you would like some more details, as I've just presented the main results here. But if there's anything you take away from this, is that we think that the emergence is more passive than active. There are certainly active components, but it's more passive. We think that the supergranulation is likely to be playing a large role. So moving towards tighter constraints, we would like to look at the motion of polarities in relation to the flows. So we've looked at these a little bit separately at the moment. And is the Coriolis force responsible for the tilt? Then, as it's a function of sign and latitude, this seems to be the case. But what east-west flow is it acting on? And of course, we would like to do quantitative comparisons to other numerical models. So I will leave it there. I will be happy to answer any questions. Thank you for your patience with my technical difficulties. And thanks again to the organizers.
Thank you, Anna. So we have a couple of questions. Dipendra, your question.
Yeah, Hannah, that was a nice talk. I think there's a lot of physics hiding in your observations. Intelligently done. So I would first like to ask if you would be happy to share the work that you did based on the inflows and the dependence on active region flux, because I am sort of right now writing a paper on the impact of inflows over much larger scales on the polar field buildup based on observations again. But we have not done analysis of individual active regions. I think your analysis would nicely complement what we're doing. I'd like to refer to your work. Second, regarding your comments that the rise of flux tubes is very passive and determined by the convective upflows. My understanding from was it Matthias's talk, I guess, was that this is true for the near surface layers when the flux tube has weakened a lot and expanded, whereas deeper down the emergence is more dominated by the buoyancy forces. Would you like to comment on that?
So this may be true that the convection comes into play near the surface with the thin flux tubes. This is absolutely correct. There are some things that don't add up exactly for me, so I'm open to modification of the thin flux tube with the addition of convection. So for example, the tilt angle, Joy's law, I can imagine that if the thin flux tube, if it's happening in the thin flux tube picture where the flows are acted on as it's rising and it has that tilt, I can imagine that the convection would cause the statistical variations we observe. But if we average, we would still be seeing that tilt angle, and we're not. So Joy's law, at least, I can't reconcile the observations with that yet. But certainly if the flux tube is becoming weak enough near the surface where the convection can then pick it up and bring it up more passively, I'm completely open to this picture. Yes.
One last question by Arnav.
Yes, so I wanted to ask a question about this time evolution of Joy's law after the emergence. And more than 20 years ago, I think Robert Howard looked at this question very carefully using the data of Mount Wilson Observatory and also I think Kodaikanal Observatory. So he had a very large data set. He looked at many, I think several thousand bipolar sunspots. And his conclusion was that when they emerged, the tilts were random and in a time scale, if I remember correctly, some 4.3 days or something like that. In that time scale, I think it relaxed to Joy's law. So whereas you are saying that initial tilt angle, instead of being random, it is like east-west oriented. Of course, your data set is much more limited, only 154, whereas Robert Howard's data set was, I think, many thousand, bipolar sunspots. So would you like to comment? What do you think?
Yes, I would very much like to comment on this. So yes, that sample is much bigger. The difference is in that we are measuring the magnetic field and we are capturing the emergence when the magnetic field is not yet strong enough to cause a darkening in the continuum. And traditionally, these measurements by Robert Howard and so on from all these observatories are typically from the continuum. And when the darkening occurs is 1 to 2 days after what we are calling the emergence time from the magnetic field. So if you go, the magnetic field is a tracer where we can trace the emergence back before you can see it in the continuum. So this is really capturing closer to what I call the moment an active region starts to emerge. So these previous observations are completely in line with what we observe because the intensity is not there until 1 or 2 days later, which is exactly when we see Joy's law set in.
Okay, well, you are saying that it is consistent. That means that after 2 days after what you call emergence, there would be a phase when there is a large amount of scatter and then it converges to Joy's law. Is that what you are finding?
There's still a huge amount of scatter. The scatter changes as well. There's still a large amount of scatter in the tilt angle at the time I call emergence, and then the scatter decreases.
Okay.
So the scatter in the angle decreases with the time as they all sort of tend to obey Joy's law.
Okay.
Thank you, Anna, for this talk. And I'd also like to thank all the speakers of the session for maintaining the timings and for their interesting talks.
Yeah, thank you, everyone. So please keep your video on. It's going to take a screenshot. Hold on for 1 or 2 minutes until our LOC person finishes that. Okay.
It's one there, Nagaraj.
It's done. Rajguru sir, it's done.
Yes. So I think it's done. Thank you. Hi everyone. So we have a break for about 15 minutes. We'll come back at 11 a.m. Indian time. So we have 15 minutes. So the next session is on synoptic solar physics. See you all back in 15 minutes. The Zoom will be on.
You can pause the recording now.
what is usual cycle then? When we talk to some people, we often say, well, it's a typical sunspot, it's a typical flare or filament. Again, how do you know what is typical? We also heard that there is this tendency, and you can see in the low part of my panel, you can see sunspot numbers, and you can see this red line that seem to imply that there is a long-term decline in solar minima over several cycles. And so the talk was, well, solar minima become deeper and deeper, and maybe sun approaches new grand minima. Again, how do we know that? And this is something that we need synoptic long-term observations for. This data allow us to benchmark, so provide a reference for what is a typical or normal state of a natural system. In our case, it's the sun. Then it also provide data for studying systemic changes. Sun as any system evolves with time, changes with time. So what are evolutionary and non-evolutionary changes in this natural system? And then taking data today, we really, unknowingly probably, we, accumulate data for some future researchers. It's an exploration. Somebody will ask questions we don't even anticipate today, maybe 10, 15, 20 years from now. And if you don't take this data, somebody will wonder why we didn't take this data when we could. Over the years, we accumulated lots of historical data, all different type. And so you can look at very simple early data that include sunspot numbers, sunspot drawings. These data sets go to back to 400 plus years. More recent data have more information, and this data include, for example, full disk observations in a selected spectral lines. Calcium K line was one of these lines that early observations started at Kodaikanal and then continued at Mount Wilson Observatory in the US. In early 1970s, also at Mount Wilson Observatory, they started the systematic measurement of magnetic field strength and polarity in sunspots. And this data set continues through present. Then there is a long record of chromospheric filaments in prominences. This could be photographic data or drawings. And we have, photographic data and drawings of early solar eclipses, and so on and so forth. More recently, we have more objective data, radio observations, for example. Still, this data set is about 75 years old now. So it is a synoptic long-term data set. And we can go to, even further in time, deeper in time, and use non-direct records of solar activity, such as cosmogenic isotopes in the terrestrial archives, like ice cores and tree rings. This early data, historical data, have several problems, several issues. The main problem is non-uniformity. So if somebody observed the sun over 150 years, there are inevitable changes in instrumentations. Different observers changed. And there were observers who had to learn these observations, or more experienced observers. So there are learning curves or even subjectivity. The more modern data, unfortunately, lack that continuity, because the way the more recent scientific research operates, it's aimed at rapid return. So there is no, with few exceptions, there are no well-planned synoptic long-term observations. The exceptions are, of course, Mount Wilson not Mount Wilson, Wilcox Solar Observatory. There are data from GONC for about 25 years now, and there is a long-term time series of full disk vector longitudinal magnetograms from NSO. Although this data set is also non-uniform because of, over the years, multiple instruments were used for this data set. So what this panel shows is all measurements of magnetic field in sunspots from 1917 in upper panels for Mount Wilson Observatory. Then in 1957, about 40 years later, similar observations started at Crimene Observatory, and that's panel B. And the panel C shows in a black color, it shows observations from Pulkovo Observatory. And the blue color is some observations. I just didn't have time to put all observations from the Potsdam Observatory. Data set at Potsdam starts in, I think the first measurements in 1944, but more systematic data are from 1946. So looking at these data sets, you can see that examples of non-uniformity. So you can see that Mount Wilson, until 1960s, the observations were taken with the same telescope, same setup. During that time, they changed about 4 or 5 spectrograph gratings. But then something happened in 1965. The instrument was changed, the grating was changed, and as a result, the measurements shifted to different spectral line in different spectral order. They had to replace the tip plate that they use for measurements. In the result, you can see the upper limit. So the magnetic fields couldn't be measured more than about 3,000 Gauss, 3,500 about. At the same time, there is this curious development of the gap for weak fields. And you can see similar gap is present at Crimene Observatory, but it started earlier. At Pulkovo Observatory and Potsdam, there were no gaps for the weak fields. What I see as a reason for development of this gap is the development of our knowledge about sunspots. So in 1960s, from the plasma physics, we learned that sunspots cannot be weaker or weaker than about 1,000 Gauss. And so that knowledge started affecting measurements. So we've, observers start looking at field strengths and trying to measure it, well, accordingly. So that's the subjectivity that not obvious, maybe at first. And then you can see other subjective developments later. You can see that there is a slight decrease in field strength, more and more weaker sunspots measured at Mount Wilson Observatory. But unfortunately, we cannot verify that with Crimene Observatory data because they artificially imposed the low limit for measurements. And so everything below, 1,000 Gauss is not measured anymore. So this is subjective non-uniformities that we need to deal with when we work with the historical data. And to mitigate this, we really need to think about, homogenizing the data. And there are different approaches. There is a nice recent paper by Yerelmin Lim et al. And using neural network and machine learning. Then there are previous studies. Theo developed this method, photometric calibration of calcium K data, normalizing them, excluding the artifacts. Then you can also assume certain properties, constancy of certain properties. Like in our paper, we assume that the core intensity in calcium K-line images correspond to the network. And so the assumption was made that network doesn't change, the properties of network don't change. And then you can scale everything in such a way that you scale that network properties to some standard profile. And you can see that how it improves the representation of data. Now we can see the cycles much better. And you can see clear difference in distributions of intensities for time of solar minima and solar maxima. So this kind of mitigation, homogenization of data could be done prior to using the data for scientific research. And of course, we can do cross-correlation between data sets and look how well the modern data correlate with historical data. And again, there are several studies that show that. And sometimes you see linear relation. In this case, we looked at magnetic field measurement, vector magnetic field measurement from SOLAS, HMI, SOLAS VSM spectral polarimeter. And this is this classical observations of magnetic field strength at sunspot from Mount Wilson. In this case, this observations from Crimean Observatory and in comparison with HMI data and SDO. And you can see there are correlations. So historical data do represent, modern measurements quite well. Now, with all of this said, what we can learn about synoptic observations? And in fact, we did learn a lot in the past. So we can represent and understand the level of solar activity, kind of sunspot number, solar cycle. We can study the properties of solar cycle, amplitude, period, latitudinal progression, like in this case, butterfly diagram from the calcium K observations from Mount Wilson. Then we can study properties of active regions in respect of the tilt, polarity separation, differential rotation of the sun. We can combine this historical data with modern numerical techniques and model something that we didn't measure at the time. Like in this case, this is from Eero Virtanen PhD dissertation picture from representing large-scale magnetic fields in the sun from about 1917 through 1985. And you can see that, how we can model polar magnetic field during that time using historical data, even if we did make this measurement. And so when I look at this, some of these properties, these measurements that we did with historical data, I seem to arrive to some surprising conclusion that the solar activity over the last 100 years does not change that much. And it is surprising in some way, if you say, well, wait a minute, if I look at sunspot numbers, there are all kinds of sunspot cycles, big, large, small, short, long. How you say that there is no, they're all similar. The cycles could be different in amplitude, in duration, but if we parameterize them, they look very similar. So what I show here is the declining phase of all cycles that I could get from sunspot number, and they all parameterize to the declining phase. And you can see that majority of them actually form very tight, family. There are few different from other cycles, but most of cycles are very similar in declining phase, and the same for rising phase. Again, if we parameterize them, so there are differences in scaling, of course. Then if you look at the solar rotation, and the typical representation for solar rotation is, using this A, B, and C coefficients in sine, cosine, or sine and sine square functions. And you can see that C and B coefficients very close to each other. And so that suggests that they're not independent really. And so if you orthogonalize this coefficients, if you exclude that dependency and compute independent A, B, and C coefficients, you actually get very little variation in solar rotation with time over the last 75 years. So again, to me, it says that, well, there is not that much change over last 100 years. How about the magnetic field? And you know, if I assume that you know, different observers probably measured quite well large sunspots, and small sunspots, you know, were measured with significant errors, then I can correlate this data sets from Mount Wilson and more modern data. And what I see is the typical sunspot, the field strength in sunspots, it didn't change over this, you know, 100+ years. This is average, right? But you know, you can ask, well, in the past we used to see very large sunspot, you know, field strength, and indeed at Mount Wilson data we have field strength, you know, several measurements 5,000 Gauss, and the record measurement is 6,100 Gauss. Huge sunspots. But remember, in the declining phase of cycle 24, this unusually low cycle, actually Hinode measured very similar field strength, 6,250 Gauss. So again, to me, it says there is not that much change. And we can even go, you know, back in time, because before even the magnetic field was discovered in the sun by George Hale, several astronomers measured what they called the line reversals. And you can see the example of this line reversals, which nowadays when I look at this, I said, oh, that's the Zeeman effect. It wasn't recognized at that time, but rather these measurements in published papers, which you can actually convert to field strength using known lambda factor, and that broadening, that reversal, as they call it. And the field strength about the same as we measured now. So again, over 120, 150 years, sunspot didn't change. And so we can continue with this. You know, we can also use you know, sunspot as proxy of magnetic field. And if you look at this, you know, we can clearly see double distribution of magnetic field and by areas. And here's a combined distribution logarithm of area of sunspot and field strength in that. And if you plot these distributions over the cycles, you can see that the component with strong magnetic field sunspots doesn't change over these cycles. What changes is this weak field, you know, small sunspots component. And then the question is, what does it mean? Does it mean that there is a you know, distributed dynamo, that we have, you know, clearly one layer where the strong sunspots form and small sunspots form somewhere, you know, higher up
you have 5 minutes more.
All right. Or it could be, you know, indication of dynamo and dissipation, or it could be, you know, dynamo in deep layers and near surface dynamo. So again, this is something that synoptic data really help us to show. I should really rush through all these slides, but you know, to give you idea of other aspects that we could see with this data, you know, this Joyce law, the tilt of active regions. You know, we look at a similarly known dependency with latitude, and you can see that there is a difference in you know, non-zero offset for the equator between odd and even cycles. Again, what does it mean? You know, polar flux, we cannot see it very well from the ecliptic. We know that it's important, but using the long-term observations, we actually see how the polar fields reverse, you know, with time. Let's see, is this? No, it's not going to play. All right. Well, anyway, so we can go through these examples, and actually learn, lots of about the polar field, even if you don't see it very well. Magnetic helicity, there's more modern data with vector field, and we can see the patterns of hemispheric patterns, which seems to be different for cycle 24 now. We don't know for previous cycle or next cycle. Hopefully for next cycle we'll know that. But it's not simply north-south hemisphere, but there are some in large scale helicity there are some patterns that change in sign in some phase of the cycle. And I'll skip that one. And so what's synoptic data good for? So they provide this bigger picture to us as a context imager. It also provides a long-term history of events, which may reveal some surprising trends. And so when I look at these trends, and I hope I convinced you by giving examples that it seems that property of solar activity and property of solar cycles do not significantly change over the last 100 years. And somehow it's not surprising because, sun is, the 100 years is just a blink of an eye for the solar activity, for the solar revolution. And so I'm not surprised that we don't see the change over this period of time. So I think I'm up to my time now. Thank you for your attention. And I have another 1,000 slides, but I'm not going to show them. Thank you.
Thanks, Alex. So I would be handling the question answer session. So any question, please raise your hand and you can unmute yourself and ask the question to Alex. Yeah, Deepankar, please go ahead. Yes.
Thanks, Alexei, for providing you this overview. But this last statement, the solar activity, of course, it doesn't change if you look at it a very longer time scales of 1,000 years. But now the Dynamo community or the modelers, they need to know these fluctuations, what you call it. And I think it is important for us who look at the synoptic data to identify those fluctuations. I mean, whether it is the scatter in the tilt or meridional circulation or differential rotation, it's a tough task because of the errors in the analysis. But I think those are very crucial elements, and I think we have to provide that to the community so that the asymmetries or the smaller changes what you see within the even last 100 years can be explained. So I think big task is ahead of us.
I agree. I mean, the modeling now is at the stage that they actually can use this perturbations or fluctuations, and from the data provider side, I think it's critical to remember. I started from this, how much the non-uniformity we have in the data. So we have to be very careful to take this into account. Then the fluctuation that we determine are real, not because of some of the subjectivity and non-uniformities.
Yeah, that's absolutely right. So our task is more difficult to make the data more reliable and identify those fluctuations. Yeah.
Okay. Next question is from Devendu. Devendu, please go ahead.
Hi, Alexei. So there was some results, if I recall rightly, which talked about a decrease in the mean magnetic field strength within active regions, a secular decrease. Do these results still hold?
So you're referring to this finding that Bill Livingstone and Matt Penn claim that there is a decline in magnetic field. No, there is no such thing. If you look at one of the plots that I showed, what they found was really unfortunately coincided with this period from short left before the maximum of cycle 23 and through declining phase of that cycle. So that was the decline they measured. And I think later, and then you can see that later it reversed and changed direction. There were later papers that demonstrated that no, there is no such decline.
Okay, great. I think that makes sense.
Mm-hmm.
Yeah, Vidya. Yes.
Yeah, I mean, so at some point you're saying that the bimodal distribution of sunspot, and then also you talk a very little bit about this tilt. So I recall one of your paper, although you did not discuss that one. So there you are saying that if you study the tilt of BMR based, different BMR based on their field strength or area, and if you find that the smaller BMR, like this, you call the quiet sun BMR, and the ephemeral region, they show completely opposite tilt, opposite trend of the tilt. Okay, like I guess it is like so-called anti-Joyce relation you find. So my question is, do you sort of like still believe that result is very robust? Because I think the result is published maybe 10 years back. Yeah. So would you like to make some comment on this?
Yeah. So in that paper, what we found was that if you look at larger, bipolar regions, they all exhibit, tilt typical for this solar cycle. Then you go to much weaker magnetic fields, and at some point they distributed almost randomly. So it's almost like random encounter. Two poles come together, and so you look at circular distribution. It's all almost symmetric in all directions. However, in high latitudes, we found this oppositely directed weak fields, and I think the idea was that what we see is this extended cycle. So we see, bipoles oriented, but not for this cycle, for the next cycle. So that was the idea that we, in the weaker fields and high latitude, at some point we start seeing orientation that corresponds to the next cycle. And I think it's still true, still holds.
Okay, good, thanks.
Mm-hmm.
So we do not have time for any more questions, but if any of you have a question, please post it on the Slack channel and for the further discussion. So let us thank Alexei once again for the excellent talk. And over to you, Sindhuja, for the next speaker.
Yeah. So the next speaker is Professor Jagdev Singh from IEA. He'll be talking about the Kodaikanal synoptic programs, historic and modern. Professor Jagdev Singh, could you please share your screen? This is a 20-minute talk, so 17 minutes for a presentation and 3 minutes for discussions. So I'll be giving a warning at around 14 minutes.
Okay, Sindhuja.
Now you can proceed.
Okay, after the nice talk by Alexei on the general talk, my topic is very simple. I am just going to talk about the synoptic chart, Kodaikanal synoptic observation, historic and modern. So these are the two domes. One is we call North Dome and another is South Dome. North Dome, we have a photoheliograph where we have been taking the observation of the sun from white light. So general, these are the synoptic observations which we have taken from Kodaikanal, broadband images of the sun since 1904, calcium K spectroheliograms. We continued from 1905 to 2007 when the films were not available for recording the data. So the observation was stopped in 2007. Then H-alpha spectroheliograms we have been taking from 1912 to 2004. So when the films were not available, then we switched over to the CCD cameras and other things. So then spectroheliograms in the chromosphere in H-alpha
were also taken to study the prominences. So we were blocking the sun and recording the outer atmosphere of the sun to study the prominences, sometimes in H-alpha, sometimes in calcium K. Then calcium K filtergrams of the sun was taken from 1997 to 2007. So that we use this cytostat itself to record the images. But later on, we installed a twin telescope. There were two, I'll discuss a little more about the twin telescope. Then we got another telescope, H-alpha telescope, to take the filtergrams from 1914, that is being still taken. Then calcium K line profile of the sun as a star, 1969. Then calcium K line profiles of the sun as a function of latitude and integrated over the visible longitudes from 1986. And these are taken on daily basis whenever the skies are good, permitted. Then I will talk about new methodology to calibrate the historic calcium K images of the sun. So these are the white light telescope. This telescope takes the white light picture of the sun. The size of the image is 200 mm, plus minus couple of mm, depending upon the seasonal variation. Aperture is 15 centimeters. Operation from 1904. It is still being taken in. So it is not that data is just taken and stored. Lot of research topics have been taken up in the past and presently also. Study of solar activity and its variation, white light faculae and the cycle prediction, study of solar rotation and differential rotation, variation of solar rotation with solar cycle phase, rotation image of the young spots, rotation rate of the well-developed spots, that older spot, correlation with the calcium K index, UV, etc., white light faculae and climate for the climate change, variation in the tilt angle. All these topics has been addressed. Extensive studies were done by Shivaraman and Howard and Gupta. What they did is they digitized all the images, and they did not digitize the images, but they only measured the sunspot positions on the images, and then they carried on for almost 20 years studying the sunspot data and other things, etc. Then Munir and Singh studied the tilt angle of the sunspots, and they found some departure from the Joyce law. Paper is published in Singh and Prabhu used Javdaya, Hiremat, Foucault, and many other people have used this data. Probably Dipankar will talk more the details. Then we have a H-alpha spectrograms. So this was used. H-alpha spectrograph was added by Evershed in 1912. And since when we got only calcium K line spectrograph, and then he built H-alpha spectrograph and added to that. So 1912, we are taking on daily basis up to 2004. Then films were not available, so we stopped. So such topics which were taken up, study of solar activity, flares, prominence of filament, dynamics of filaments, and solar cycle phase, heating of filaments before disappearing, magnetic neutral lines of large-scale magnetic fields and solar activity, poleward migration of the magnetic neutral lines. So this was done by, lot of studies were done by Shivaraman and Makarov. They did over almost 20 years. They used the data for 20 years from 1912 to 2003. And Singh, Gupta, Sundarama, Alim. But one thing is noteworthy is that long back, about 70 years back in 1952, Anant Krishnan studied the prominence and reported rush to the pole. So he found that prominence is rush to the pole, what is now known as popular. This was pointed out by Gopal. Thanks to Gopal for pointing out these things. Now I talk about calcium K line spectroheliograms, which were started in 1905, and they were taken up to 2007. So this was used study of variation of calcium K network sizes with the solar cycle phase, Singh and Papu. What we were interested was this, since we wanted to see the global change in the network size. So we always studied all the network sizes away from the active regions. Okay, this was done manually. At that time, we did not have the computers to do all kinds of work and even the softwares. So this was done by manually. And we have measured over 11 solar cycle, and each solar cycle about 5,000 network sizes was measured. And then variation of calcium K network size with latitude, Raju and Singh, they did. Variation of chromospheric activity has been done, studied by many people, Talatov, Singh, Mutuptel, Ravindra, Kriappa, Raju, Fokal, and Moli, and many others. They have studied the chromospheric variation, the chromospheric activity. Then variation of small scale activity using EN, enhanced network, active network, and quiet network by Singh, Mutuptel, Ravindra, and others. Now, variation of places, enhanced network, active network, and QN as a function of latitude and implications to meridional flows. And that has been done and by Pooja, Chandra, and et al. This paper has already been accepted in Solar Physics, has actually appeared. Dipankar may talk more about it. Okay, now the modern or the today what we are going to do, we are in operation at Kodaikanal. One is twin telescope, another is H-alpha telescope. Twin telescope is two 6-inch telescopes which are identical, and then two CCD cameras. And they are one is used for taking white light images of the sun, another is taken calcium K line images of the sun. And this some work has been done by Singh, Mutupte, and Ravindra. Then H-alpha telescope, which is in operation in 2014, and it is 8-inch telescope aperture, and passband is 0.04 angstrom, and number of images are taken every day, and Ravindra has done some work on that. Now, chromospheric variability of sun as a star. In 1969, Bapu started monitoring the calcium K line profiles of the sun as a star. And when I joined him in 1974, he told me to continue these observations on daily basis whenever the sky permits. Okay, Livingston started in 1974, and Kale started in SACPIC in 1978, similar studies. Data of Livingston is much better, stable, because spectrograph is stable and his photometric accuracy is much better. We have been recording the data in the beginning at using the photographic film, and later on around 90s, we started using the CCD camera for recording. Singh started the monitor the calcium K line profiles as a function of latitude and integrated over the longitude. Since 1986, when I was analyzing the data of the sun as a star, I realized that we can do better if we study the calcium K line profiles as a function of latitude and integrated over the sun, integrated over the longitude. So Sindhuja et al. Has used this data and studied its implication on the meridional flow. And they found that there is a variation in the speed of the meridional flows with the phase of the solar cycle. Beginning it is faster and then slowly it goes down. So now the thing is, we have developed, since there is a lot of scatter, people talked about, that while studying the data of calcium K images, then they find that there's large variations. I'll talk about it. So we have developed a new methodology to calibrate the historic calcium K spectroelograms accurately. This paper has already appeared in APJ just a few days back. Okay, so we digitized all the data of the sun, calcium K, H-alpha, prominences, whatever data was available using 4K by 4K system. This was digitized units was a developed indigenously, and then we analyzed the data and studied the Plages enhanced network. We were able to separate out all the Plages enhanced network and the other networks like active network and quiet network. Now the problem is we have three kinds of images. Okay, as Alexi already pointed out, observer chains, different instrument at different things. Okay, so there are changes in the contrast of the film of the data. Okay, so this is a high contrast image which is taken to the minimum phase of the solar cycle, and there is hardly any Plages region. But if you look at the intensity distribution of that, it indicates there is a significant larger area which comes under the category of Plages. And if you look at this image, which is low contrast image, and there are large number of Plages, but the intensity distribution of this image, flattened image indicates there's not much area which is comes under the category of Plage areas. And this is a normal contrast image where the intensity distribution lies between the low contrast and the high contrast image. Now, the different contrast happens, different passband and shift in the passband of the calcium K line in case of spectroheliograms. So they causes the change in the contrast of the images. Images taken towards the blue wing of the calcium K line show more contrast. Larger passband decreases the contrast of the image and shorter increases the contrast of the image. May remain same for the instrument. If the instrument is the same, it may remain the same, but there are other factors which changes the contrast. Change in the emulsion of the photographic film causes the change in the contrast. Even freshly procured and stored film, old film produce different contrast images. Change in the chemicals and the development environment such as temperature and causes contrast change.
Sorry to
Sky
interrupt, you have 3 minutes more.
Okay. Sky condition, presence of thin clouds causes a decrease in the contrast and other things. So the different contrast of the image leads to uncertainty into the determination of calcium K line features such as Plage network and areas. So what we have developed is we have converted all the images into equal contrast images, what we call is ECT. We redefine the intensity of each pixel. I is the intensity of the IP is the intensity of the flattened image, and then we gamma is the contrast of the images. So we measure the full width of a maximum of the image, and if it is lies within 0.1 to 0.11, then we take it as a normal contrast image. But if the full width of the intensity distribution is greater than 0.11, that means it is high contrast image, which decrease the gamma of the gamma factor, and then otherwise we increase the gamma factors. So what we do is, you see the high contrast image, this is the intensity distribution. But once we make it equal contrast image, the intensity distribution becomes like this. And this is a low contrast image. Then again, we change the factor of gamma. We recalibrate the images, and then we do this. But one thing one need to make sure that before applying the gamma, image should be flattened properly. If the images are not flattened properly, that may instrumental effects are not taken care of, then it will not work. Okay, now you see earlier analysis, since earlier monthly data is available about the calcium K Plage areas only. So we have compared our data of ECI images, equal contrast technique, with the other data. And we found that the whole set of data, about 2/3 of the images were okay, and 1/3 were good images, and 1/3 remaining data was not good images. I will not be able to give full details. What I would like to point it out see focal and data, the correlation coefficient between Plas-Arian and sunspot numbers was 0.66 and Talatov, etc. was 0.6. But it has equal contrast images, it has become 0.9. So it has improved a lot. Okay, so these are the Plases. Top shows the Plases before we apply the equal contrast technique, and you see large number of quite a bit significant scatter. But once we apply equal contrast image technique, the scatter goes down. And it is not only the scatter goes down, correlation coefficient improves a lot. What happens is even the relation between the sunspot and the Cassion-K Plas areas also changes. So that is the major factor which one need to consider. And then if you talk of the small features like active network and small scale magnetic field, it is almost impossible to measure the scales, study the variation of small scale magnetic field because the correlation is very poor, scatter is large. But once we apply equal contrast technique, you see a very smooth curve kind of a thing. But at the same time, one may note that when the sunspot number increases beyond 250 or so, up to 250, it is almost a linear relation, but it almost gets saturated after 250. Sunspot number goes, relative number goes to more than 250. Okay, so these are the, again, I have shown equal contrast images technique. We can study the all features like active network, quiet network, and other things, etc. And if you look, then this correlation on a daily basis. Previously, people have been studying all the correlation between the sunspot and Cassion-K Plases by averaging the data over months and years kind of a thing, etc. But we have studied the correlation of daily basis. All those plots I show is on a daily basis for the 100 years of data. There's no averaging of any parameters. These are, and we can study the variation. We find the not only the Plases, but the quiet network and the active network also vary with the phase of the solar cycle. Okay, so we have developed a new methodology to analyze the historic photographic Cassion-K images of the sun accurately. The ECT technique, equal contrast technique, takes care of the uncertainty in the density to intensity conversion, changes in the photographic emulsion, changes in the contrast due to the shift in the passband, development environment, changes in the sky condition also. For the first time, we have been able to show day-to-day correlation between the Cassion-K line features and the sunspot data. So far, Plas areas and Cassion-K index variation have been studied by averaging the results of measurements over several months. What we have done on a day-to-day basis, we have studied EN and AN and QN colloidal fields in addition to the Plas areas for all the 100 years work. So we plan to analyze, actually I will go to the next slide. We plan to study the variation of in Cassion-K line features as a function of latitude and its implication to the meridional flows. Last slide I'll show you. This is the data. We have taken Mount Wilson data, PSP data, and filtergrams taken at Kodaikanal. So you see on a daily basis, previously and generally people have found out that Plas area determined from the Mount Wilson data are appreciably larger than the data measured from the KO, Kodaikanal Observatory. The Plas area measured from the KO, Kodaikanal Observatory showed much less areas as compared to the Mount Wilson data. But after doing equal contrast technique, you find that the areas measured almost same. And there's a good correlation. We are doing more studies. We are doing the detailed studies of these things, etc. And probably in a couple of months, we will be able to complete the analysis of this data. This blue is Kodaikanal data itself. And what these are filtergram data. And this is low contrast when the detector was small, and this is high contrast when detector was large. Thank you very much. Hello? Any questions? Sindhuja?
So there is no, I couldn't see any raised hand. So is there any questions?
Yeah, I'm sorry. I think there was a disruption from my side. Yeah, one or two quick questions we can have. Yes, Rakesh, go ahead.
Yeah, hello, Jagdev sir. This is a nice talk. Yeah, I was just wondering about the new telescope, which now you showed, twin telescope, and also this new H alpha. So will they replace the existing one? And in that case, the cross calibration and everything has to be done for the to get the data in the same level, like one-to-one.
See,
yeah.
The thing is, once you do the equal contrast technique, we don't need the kind of anything else.
Okay.
We don't need the superposition of the data. Actually, for 2000 to 2007, we took the filtergrams. This is 2000 to 2007. At the same time, we had the spectroheliograms also.
Right.
So I thought of that we should have a common data, two sets of data with a common period.
Exactly.
But with the equal contrast technique, we don't need that. Since we white chromosphere makes it similar. If you go back, you see, if this is the white chromosphere. Okay. So this becomes almost similar.
Exactly.
Identical. So once you make this identical, and by adjusting the intensity of various pixels,
exactly.
So you don't need any other calibration. So this takes care of all the factors which we have been struggling about for a long time. For a long time, we have been struggling how to do. Even the intensity calibration, when we talk about it, and that is not complete. All the data does not have the intensity calibration. Another thing is intensity calibration also is not perfect. It has a lot of errors. When I was trying to do that for the individual plate, individual calibration curves, then I found that it adds much more error than even instead of compensating the intensity calibration kind of thing, etc. So we had to use the average calibration curve to analyze the earlier data. So you're right. So we don't need any other data.
Yes.
Actually, that is what I showed. It can be so it is different data. Mount Wilson data has a Mount Wilson data as a pass band is about 0.5 angstrom or 0.35 angstrom. Sometimes they have been changing the pass band itself, but Kodaikanal has a 0.7 and filtergrams have a 2 angstrom pass band. But still we could combine all the data sets to study the plasmas. So and this PSPT has a different pass band. It is about 1.3 angstrom or so, but ours is 2.5 and 2 angstrom, but they produce the similar results. So we will be able to combine all the data from different observatories with different pass band, with different, there might be some small uncertainties, but by and large, we will be able to combine data.
Okay,
so,
thank you.
We do not have time for any more questions. If you have any question, please post it on the our Slack channel. And next we go to the.
Thank you.
Thanks, Jagdev. Yeah.
Thank you.
So Sindhuja, you can go ahead with the next speaker.
Yeah, our next speaker of the session is Dr. Alexander Madvinov from ISTP SBR RAS. He will be talking about the multiple reversals of the sun's polar fields and their physical causes. Dr. Alexander, can you please share your screen?
Yes,
Professor Jagdev Singh, can you please unshare your screen?
Yes.
So that Dr. Alexander can share his screen. Professor Jagdev Singh?
Maybe our host can do that.
Okay.
Yes.
Okay.
Okay.
Dr. Alexander, you can please share your screen now.
Can you see my presentation?
No, we couldn't see. Yeah. Can you please make it full screen?
Okay.
Yeah.
Is it okay?
So I'll be giving a warning at 10 minutes for you. You can go ahead now.
Yes. Good morning, colleagues. My name is Alexander Mordvinov. I will present the results of joint research. Introduction. However, Alexey Pevtsov told all things. Nevertheless, synoptic maps are suitable to study active regions, unipolar magnetic regions, surges of resonant flux, and we reconstructed magnetic fields using the calcium and H-alpha synoptic maps from Kodaikanal Solar Observatory. We used also magnetic flux from KIT-Peak, and we reconstruct magnetic fields using empirical regression relation between the calcium intensity and unsigned magnetic flux. Signs of magnetic flux were accepted according to corresponding maps of dominant polarities derived by Makarov and Sivaraman from Kodaikanal Solar Observatory. This is an example of such synoptic maps, and chromospheric filaments outline large-scale magnetic patterns, and dominant polarities are labeled by plus and minus sign. We digitized these maps in such a format and quantified dominant polarities with plus or minus values for cycles 15 to 19. We are grateful to many people who observed and prepared this data for scientific community. This is another example, synoptic maps of magnetic flux density from Kodaikanal, and in gray scale, calcium plates are indicated by yellow contours. These appear above active region. We also see a red arrow indicate surge of magnetic activity, which originate after decay of active regions. This, and this. In the next panel, we see the calcium plate synoptic map and absolute value of the flux. Green contours indicate absolute values about 20 Gauss. And bottom panel show signum of flux shown in black and white, and the polarity inversion line are also indicated by red contours. we estimated regression relation between unsigned magnetic flux and calcium emission. We used robust algorithm LOVES, developed by Cleveland. It is a very good algorithm, and estimated the empirical regression. It is shown by red curve, and the confidence level limits. We applied this algorithm to many Carrington rotation and plotted generalized models which show the regression relation between calcium emission and magnetic flux for different levels of magnetic activity. The first panel show regression relation for low magnetic activity. And this one show the regression relation for high magnetic activity. Both curves have consist of two parts. This part, in this part, magnetic network, calcium network, make significant contribution. This part, calcium plates. The same is here. Using the regression relation, we reconstructed magnetic field for cycles 15 to 19. This is plot show the upper panel show change in sunspot area in the northern hemisphere, the lower bottom in the southern hemisphere. What see in the middle bottom is time latitude distribution of averaged magnetic field. Every synoptic map, we averaged it over the longitude, and this latitude, extent show zonal panel, zonal structure of Carrington map. Then we arrange this profiles chronologically, and this distribution show evolution of magnetic fields over 5 cycles. We paid special attention to polar magnetic fields in relation to low latitude activities. So every cycle is shown by butterfly diagram. Black contours show zones of intense sunspot activity, and we see that after decay of activity region complexes, surges of remnant flux originate. These reach polar zones and led to polar field reversal. This map, these surges are labeled by N19, N2, and 3, and 4, 5 levels. These are critical surges in the northern and in the southern hemisphere. This picture corresponds to a Babcock-Clayton scenario. However, there are sometimes reading of surges of leading activity arise. For example, in cycle 16, after the critical search of following polarity arose search of leading polarity. It originates in areas where non-joy active regions were concentrated. After decay of non-joyous active region, mirrors of leading polarity appear at larger latitudes, and these regions are transported to the pole and led to the second reversal. And the dominant polarity changes during this time. The next decay of active complexes resulted in next search of following polarity. So in the cycle 16, dominant polarity changed 3 times. Similar situation was in cycle 19. Sorry. Here in cycle 19, we
Can
see
you please
also
make it full screen? You have 2 minutes more.
Sorry. So this picture corresponds to Babcock-Clayton scenario. However, we found new type of surges. These are shown by dotted arrows. By the end of every cycle, unipolar magnetic region of leading polarity concentrate near equator. Then during the period minimum activity, these surges are transported and reach mid-latitudes and meet here new surges. These surges merge and enhance polar transport of the same polarity. So we name these surges as final leading polarity surges. These surges strengthen following polarity surges in the next cycle. These surges link together 2 individual cycles in pairs, and thereby these surges suggest possible long-term memory in solar activity. Next slide. To evaluate quality of our reconstruction, we estimated polar magnetic fields using integration in polar zones. These curves show the results of comparison. The solid lines show polar fields in southern and northern hemisphere, and dotted lines show indirect indexes of polar activity, polar count, polar factor count, and index A introduced by Makarov, and polar network index PNE introduced by other scientists. We can see that there is a good correlation of area of pair of the indices. So the reconstruction looks good. And we carried out also the similar analysis for high resolution synoptic maps obtained from MDI and HMI. The results of this analysis are shown here in this figure. High resolution synoptic maps were analyzed, and the result is presented here. Cycles from 21 to 24, and northern hemisphere, southern hemisphere. In the middle, the time longitude diagram in more detail as compared with previous analysis. We can see it is constructed using a similar technique, and we can see here in the beginning of every cycle, first surge appear, first surge of following polarity. This approached the pole and reduced the polar flux.
Sorry to interrupt, Dr. Alexander, your time's up.
Yeah. So we can see that in cycle 21, threefold reversal occurred. And many interesting details we can see in the other cycles. Generally, we can conclude we developed new methods of magnetic field reconstruction using synoptic maps of calcium and HF emission from COSO. Spatiotemporal behavior of reconstructed magnetic flux was studied in cycles 15 to 19. Major remnant flux surges and their sources were identified. We interpreted multiple reversal of the sun's polar field in terms of solar flux transport theory. The decay of non-Joy and anti-Hale Rs results in leading polarity surge that disturb the usual order in magnetic flux transport and sometimes led to multiple polar field polarities reversal. We found also the remnant flux front between adjacent solar cycles. These surges reveal a physical connection between subsequent solar cycles. Thank you. And the next slide. We are very grateful to people who observed and prepared the data for scientific community. We also used data from SDO, HMI, MDI. Thank you very much.
Thank you, Dr. Alexander. So we have a time for one quick question. So Rakesh, make it short.
Yeah, sure. So Alexander, very nice talk. And my question is like, where you see this kind of polar migration, and from that you infer next cycle. So can you by quantification, can you tell the what will be the magnitude of next cycle from this information of the magnitude of the polar migration of the magnetic field, like the what will be next cycle will be strong or it will be weak from the information you have a priori?
I presented only qualitative analysis. However, we can estimate magnetic flux.
Right. Okay, thank you.
Yeah, if the organizer allow me to make comment, I can give some comment.
Okay, go ahead, please. Yes.
Yeah, I mean, like being a co-author, of course, I can. Yeah,
yes,
so
sure.
The idea of the reconstruction of polar field is to make prediction. I mean, if you have a better understanding of the polar field, we can make better prediction of the next cycle. So yes, we can make prediction, but for the last few cycle, we have the measure polar field data. So we can use those data. Okay, so this data will be used to make better understanding of the solar dynamo, like polar migration of the polar field and like multiple reversal, etc.
Yeah, so in principle, you can predict whether it will be strong or weak. Also, you can quantify. Yeah, thank you.
Okay, so thanks once more, Alexander. Now we can move to the last talk of the session. So Sindhuja, over to you.
Yeah, the last talk of the session, we invite Dr. Professor Dipankar. He will be presenting on the new results from Kodaikanal long-term data sets. I will be giving a warning at 14 minutes.
Yeah, maybe you should give me a warning at 12 minutes. I will prefer that.
Okay.
I hope my screen is full here.
Yes, yes.
Okay. Thank you very much. I must thank Jagdev for, giving a very nice overview, which makes my life much easier. But as you see from the title, it says new results from Kodaikanal long-term data set. So I'm primarily focusing on the last 5 years. So that's the domain I am concentrating myself on this particular talk. But what I would also like to emphasize here is the multi-wavelength aspect of the digital archive at Kodaikanal. And I think, we're very proud of this archive now because it is probably the only archive in the globe which has the digital image form in these multiple wavelengths. There are many places where you have, data in terms of numbers, but you do not have the images in different levels as well. So this is just an example of, 1st January 1958. If you go, you will see an image at H alpha, you will see an image in a calcium K and white light. So this multi-wavelength aspect is actually bringing in a very new way of looking at the solar atmosphere in a historical perspective. Again, I must thank Jagdev because he has already given this overview, but just for the sake of completeness, and I have given this collage, which again gives you information that you have a fourth data set, which also briefly he mentioned, that blocking the solar disk and you can study the prominences, and majority of the time it was observed in calcium. This project, again, Jagdev, a lot of credit goes to him. He has initiated many years back, and about a decade back after his superannuation, this was handed over to me, and I have tried my best to complete this. And I think I should take little credit of making this data available to the larger community. Since April 26, 2016, it is available to the global community, and you will see the result of that. Today, I just went through the ADS and I discovered there are about 47 publications from this, Kodaikanal data over last 5 years. This is a, bar chart you see, and the data which has been used in the global map also, if you look at, it's just not restricted to India. A large portion of, US, it cuts in, all the way in Siberia. And in US also, there are many people who have this data now. Whoever has asked for the data, of course, it is downloadable, but since there are terabytes of data, I have copied over even in different levels of data. It's just not a raw data. I think Monica was mentioning it yesterday. When you are dealing with the large data, it is important that the data is prepared well. And now I would say that we are still improving our data products, but there are many data products which is available and people can straight away work with it. I also would like to point out that out of this 47 publication, I am directly involved only in 16 publications. So probably because of the shortage of time, I will only say a little more detail about where I have been involved, but I will share this publication list and all this presentation in the Slack channel, and I will request you to go through those publication lists to find out how much new results are really coming up from this Kodaikanal new archive. And this is the distribution in terms of the wavelength. And as you can see, the majority of the things have been started with the calcium and also a large portion of from white light. But these are the new two data sets, H alpha and calcium 2 blocked. It has lots of potential and we have been working with it. I mean, some of my friends in US have been working with it now. And I think you will see many more new results from that. I will quickly run through different, this 4 different data series and show what we have been doing in last, few years. We started to look at the sunspot areas from the white light data. And again, I would like to point out that this is whatever success we have is because of the involvement of large number of younger colleagues. Here you see my former student, Sudeep and Ravindra, who has enormously contributed to the digitization, data handling and so on. What we have also tried to look at is the sunspot, in terms of their sizes. And you see this butterfly diagram in the bottom, which was produced, a few years back from Kodaikanal, data alone. And of course, your always, important is to compare with the Greenwich. The correlation seems to be quite good. Although there are still challenges, and I also point out that the initial almost 20 years of the Kodaikanal data, there were problem with the data series. We have now handled that, and I will show you very preliminary results from that. So what I'm again trying to emphasize here, and I think Alexei mentioned this, that whether all the different sizes of the sunspots are coming from the same origin or not, whether the bigger ones get distributed to a small ones or the small ones collectively form the big ones. This is a question which is still unanswered. And then to look at it, we need more statistics. So this is an emphasis which we have been giving now. There are many aspects of things I will just, later on list out. But I would point out to this particular work, which very recently Sudeep has done by cross-calibrating, the data from different observatories. So there are about, I think, 15 observatory data he has, collected. And I would say that this is the state of the art, sunspot area time series. And I think it has all the information in terms of the hemispheric asymmetry, the locations, as you can see, the area distributions. And so I will draw your attention to this particular work. And Sudeep has a poster, so please look at that. This is one work which very recently been done by my student, Vibhuti, who is going to talk about another aspect until later on. But as Alexei also pointed out, we again had a relook about the differential rotation, whether we do find differences. But we find actually something slightly new here. Again, simply we looked at different sizes of the of the sunspots, and we do find that there seems to be some difference in the sizes. If you look at the areas which are less than 200 and the one which are more than 400. As you know, the differential rotation can be expressed by these two A and B parameters. A is the equatorial rotation rate and the B. And as Alexei pointed out, we also tried to look at the A and B numbers for different cycles. Since our error bars are still large, it's really inconclusive to say that there is really any variation of these A or B parameters. You see the distribution here. We try to have a look at it, but it doesn't look like we have a substantial differences. But this is a finding which was earlier reported by Shivaraman as well. And as you see here, always work need to be compared with the published data from Kodaikanal. The differences is what we are doing and today is most of the work is based on automated programs. So I have bright young minds, and they are skillful in implementing the new algorithms. We are moving into AI and ML as well, and using those algorithms, which is to some extent I prefer than the human intervention, because there is always a likelihood of a human bias when you do such work and selections and so on and so forth. But nonetheless, this is the older work which was done by Gupta and Shivaraman and so on, and the result seems to be quite consistent. Although this is a new finding, I would say, which needs to be attended further. This is a very new data. As I mentioned, we had problems with this period, and also as Jagdev pointed out, observations are being continued. So the initial series which were given from Kodaikanal was for this period within this red arrow, and now, as I said earlier, we were always comparing with the Greenwich, and I think we will have to do it with the Monroe et al. 2020, which has a cross-calibrated data series taking data from different sources. So that is what we are doing currently. So I hope this thing will come out very soon. So very quickly, the summary of the white light work. We have produced these sunspot area time series. We have worked on Waldemar effect. This was reported by Gopal in solar physics paper. We have worked on active longitude. This is an interesting area. We have heard about this terminology a few times. Sunspot size is as a probe of the solar dynamo. This was the letter paper a few years back. This is one of my favorite subject area about the double peak of the solar cycle, an explanation from the dynamo model. This was read by Vidya. We have also looked at penumbra to umbra ratio. This is reported last year in solar physics. There was also work on hemispheric asymmetry, whether you could explain this with fluctuations in the dynamo parameter. This was done again with my colleagues in Irkutsk. Variation of solar differential rotation, as you have just mentioned. Now I will switch on to the calcium K series. What I now realize is, of course, there is a lot of important issues in terms of the calibration of the calcium. There are different methodologies and so on. Now we are moving into another step. It's just not enough to identify the features, but we have to prepare this synoptic map. And we have done these Carrington maps for last 100 years. And these Carrington maps really show you the distribution of the magnetic elements of different sizes at different locations on the sun, and that been used by others very, very extensively. We have also produced these butterfly diagram. Now you have a butterfly diagram with a 3D renderation, and this you will see that again, if you do a classification in terms of the sizes of the plages, you tend to see the same behavior, that the larger sizes always seems to be only appearing in the lower latitude, and also during the close to the maxima and so on and so forth. So this is an important element which also the dynamo community need. So some of these large amount of work which is on the calcium and H alpha and so on has been done by Shubhamoy, who is a postdoc, and he has moved into a different AI domain now. But he has contributed a huge way in this. I thought I will just mention that this is a controversial, I would say, area. But if you look at the smallest elements of the magnetic elements on the sun, calcium does provide you this, opportunity. In fact, Jagdev has pointed this out. And if you just look at the network elements and try to look at its evolution across different cycles, ignore the plage areas and so on completely, then there seems to be a link or a coupling between two cycles. So these has been called the signatures of extended cycle.
5 more minutes.
Okay, thank you. So this has also been shown by combined work from Mount Wilson and Kodaikanal. This is, I think, state of the art again. Full disk calcium spectroheliograms taken from 30 different observatories over a very long period of time. We had an EC meeting. We had a big group of people who have contributed here. And now I think this is the series which people will be, using it. And as you can see, this is the longest series. Incidentally, out of these 30 series, of course, Kodaikanal makes a big impact. Also, I would point out that Kodaikanal Twin Telescope data is included in this analysis. Even the WOMP telescope data is included in this analysis. So calcium, we have generated the Carrington maps for 100 years, connection of plages with sunspots, variation of supergranular parameters in century time scale. This is all done by Shudeep, contribution of and Shubhamoy. We have also worked on the solar irradiance variations, extended solar cycle, and this is the integrated series which you see there. Now I will say that how to combine this H alpha and calcium information. We have seen one example from the previous talk where we have information about the magnetic patches, and H alpha does provide you the locations where you have the neutral lines. And I would like to again point out Kodaikanal plays a very, very important role. It's probably one of the longest series here, and probably only comparable is the Meadow, which can compete with this. One can do this butterfly diagram from H alpha. This is a very new work from H alpha. This is just accepted in APJ with some of my colleagues in the US. In fact, this was pointed out by Jagdev about this polar rush from prominence studies. This is very similar to the work. Incidentally, that Ananda Krishnan paper in fact 52 was a single author Nature paper. this is a fantastic, example and motivation for this kind of work. And as you can see here, this polar rush, this different migration rates and all that provides a very important, inputs for dynamo modelers. As I indicated, I'm repeating that combining H-alpha, calcium, and line of sight magnetogram, you can actually extract a lot more information than what people have done it before. So I will just move very quickly to the last data series, which is the calcium clay block. Again, Shubhamoy has worked this. We create the time, of course, there's a comparison with the solar sunspot number. Here we are primarily looking at the polar migration. And as you can see here, this migration polar rush, it seems to be also have two phases. This is something which we have pointed out in this paper. At early phase, there is some rate, and then in the later phase, you have a different rate. So whether that is real and whether it can be invoked in the dynamo models, there is something to look at. As I mentioned again, it is important to include the data from as many places. So this is from codiagonal prominences data. We have included Meadow and Kanzil-Hoe data. And this is what is, the right, result what we have. This is reported in this particular paper. Clear signature of poleward migration from the time latitude, distribution. And it seems to be that second degree polynomial fitted to the north and south, fits better than a linear fit. So this was our, conclusion. So again, I'm repeating that one of the unique aspects about the codiagonal data is that it has a simultaneous measurements in 3 wavelength bands. It's basically translates into 3 different heights. So sunspots, strong magnetic patches, filaments, neutral lines, plages surrounding weak fields, and prominences incubator of CMEs. So I think it is important to look at this as a collective way, and we are into that domain with the AI and so on. I would also like to acknowledge that this digitized data archive was done with IUCA's collaboration under the NKN initiative. This is a national project, and this is done on a most modern, tools and techniques. So again, as I indicated, this whatever success we have today is because of the involvement of large number of young, colleagues here. And this is a collage. You can see it's like a Zoom, snapshot. Muthupriya has worked quite extensively here, and she's still continuing in this. Manju is also working quite a bit on the H-alpha, and now with the thing. This is a new student I have who is completely going to work on AI and ML domain. And I didn't mention here another very important resource is the drawing which is there in the Kodaikanal. We are digitizing that, and we will see new results and the comparison of the drawing and the digital data. So that's my last slide. I would like to again acknowledge it's a team effort, and Professor Jagdev Singh has initiated this with a huge amount of support from my Guruji and Professor Siraj Hassan, who has given all institutional support to initiate this program. And I would also thank Arnavda, because I think because of his motivation, I got into this field. I was not, originally inclined to do this kind of long-term study. So thank you for your, attention.
Thanks, Deepankar, for giving a nice summary of the latest results from Kodaikanal data. And we have now time for questions. So we can start with Vidya. He has raised the hand first.
Yeah, I have a very quick question. So I think in the first part of your talk, you were showing the butterfly diagram of sunspot area. Very beautiful plot where you are showing the butterfly diagram, also separating different sunspot area. So you're saying that this is cross-calibrated across various data. Is that correct?
That's right. This particular example which I am showing here now, that is after cross-calibrating data sources from various observatories. And unfortunately, I must point it out, it was found out that the data series what we had a few years back from Kodaikanal was not fitting the things so well. So we are actually revisiting the Kodaikanal data series, even now with the better techniques and so on. Because it was all done by, again, quite a bit of manual intervention was there. And so we want to do it more automated way so that the human bias is not there. So this is Greenwich and, most of the places in China and, in Europe and so on.
Okay, great, thanks.
Yeah. So next question is from Irina. Irina, please unmute yourself and ask.
Hello, thanks a lot for the great talk. I really enjoyed this. I have a question about the data format. I'm sorry if it was mentioned before.
Yeah, no, I didn't mention it. It's all in FITS. It's all in FITS, but you know, we have extracted the data and some of the Carrington maps. If you are interested, we can provide you in PNG as well. So we have created the Carrington maps in JPEG, you know, because of just the data transfers and so on and so forth. So both the you know series is available, and a lot of these products are also available to you know databases. In fact, even CDS has our area series, and you know all the. In fact, the Abjay paper appendix has all the Carrington maps as well. So the Carrington maps of H-alpha and calcium is all available in the public domain.
Okay. Thank you.
Devendra? Hello. Yes.
Hello, Dipankar.
Yeah.
So I remember that we had once talked about the filament evolution over solar cycle timescales and simulate this with SFT models. So when you say that you are doing some work with some US group on the polar rush, are you already exploring this with some simulations, or is just observational stuff?
No, I didn't have time to expand it more. In fact, incidentally, it's amazing. They have only looked at the polar crown filaments and they have identified the filaments manually. Normally, I do not have that much of patience to do this. It's again, the Chinese can be only complimented to do this. So this is only manual identification of polar crown filaments. So this is the data which is taken from Kodaikanal. This is from Kanzilhoe, and this is from Big Bear. So there are data from different observatories to talk about this. But I agree, Dipendu, we haven't done that, completed that work. It's high time we do that.
Mm-hmm. And so these data are all sort of, I mean, they're available online if one wants to download this data and analyze them.
That's right. That's right.
Okay. All right,
So,
good.
Any other question, please? If not, then let us again thank all the speakers for this session, for giving excellent talks. Thanks, Dipankar. And if you have any other question, please post it on the Slack channel and have discussions there. And so,
yeah, just with your permission,
yes.
I will put my presentation and the publication list, because I must say, you know, the 47 papers, I have not done the justice to, you know, be able to talk about others. I will include the publication list also there, and I would request others to, you know, refer to those references as well.
That's great. Yeah. Okay. So, so we conclude this session, and the next session will start at 2 o'clock, roughly an hour and 20 minutes from now. So thank you very much again for participating in this session. Rajguru, you want to say anything?
No, you have already announced it. So the next session is we will close the Zoom meeting now, and we will restart 15 minutes prior to 2.
Okay.
5 p.m. Okay.
Yes.
All in about an hour.